Hello, everyone. My name is Sergio Orts. I'm a research scientist at Google, and today I'm going to be talking about our recent work around portrait relighting, which focuses on learning to relight portraits for background replacement. During this talk, I will also cover some of the details about ground truth data generation for our neural rendering techniques. In the last years, a lot of progress has been made in the research topic of neural rendering. In particular, I would like to emphasize the progress made towards relighting arbitrary images, which means that we are able to change the illumination of arbitrary renderings and photographs with the help of machine learning. There has been a great success combining classical computer graphics pipelines and learnable components, as I will be showing today in this presentation. However, the main goal from previous works didn't change, which is to generate compelling and photorealistic imagery, as we can see on this figure, where the person is being realistically composite and relit on novel background and lighting conditions. Now, coming back to our work, at a high level, what we are trying to accomplish here is, given an arbitrary in the wild portrait image, we want to relight the subject and realistically composite them into a new background. Today, we'll talk about how our approach achieves this goal. Let's take a look at our specific problem. What is our input data? As I mentioned before, it's just a portrait image, and we don't use any prior information, such as depth. Next, we assume that we are given a high-resolution HDR panoramic lighting environment, which will serve both as the target illumination for the portrait as well as the background. Taking previous works, we find single image portrait relighting. This work from SIGGRAPH 2019 introduces the idea of using a neural network for portrait relighting, treating the relighting process as a black box using a UNet-style encoder-decoder architecture. In general, this approach did a good job at changing the overall diffuse shading of the subject, as you can see here, as the color, intensity, and directionality of the illumination appear to be changing in this photo. We were really inspired by these initial results, but we wanted to be able to not only change the diffuse shading of the subject, but also to be able to add specular highlights and to be able to handle input images with strong shadows and specularities. To achieve our goal of background replacement from any arbitrary image, we mostly need two components. The first one is a matting module to extract both the alpha channel and the foreground color from the input image. And second, we need the relighting module, which takes as an input the target illumination, the HDR map, and the predicted foreground from the matting module. As expected, we use machine learning modules for both the matting and relighting tasks, as you can see in the diagram here. We use the foreground output from the first matting network as the input for the relighting network, as I mentioned before. For the compositing operation, we just use the alpha blending equation. But we also did experiment with adding a third compositing refinement module using a neural network. But we found minimal improvements here, insufficient to justify the added compute time. Next, we'll take a deep dive into the two machine learned modules for matting and relighting. Let's look at the matting module first. We call this module deep matting. This module takes an input image and a try map obtained from a core segmentation, as the one you could get using a standard off-the-shelf person segmenter. The network architecture is set up using one encoder and three decoders. One decoder generates a refined try map, which is optimized to fix errors from the input segmentation mask. That's the first decoder. Then we have another decoder that generates the predicted foreground that we will ultimately need to perform the relighting operation. And finally, one that generates the predicted alpha channel, or the alpha mask, which we will need to use for compositing. This architecture is inspired by the work from Kai et al., but we extended the proposed work to also predict foreground colors, as it has been done in some recent works in the matting literature. This model was trained specifically to work for portraits rather than generic objects, using mostly data capture in the light stage system. Compared with previous works, our matting training dataset is more realistic, as relighting allows the illumination of the foreground subject to match the background. Now, let's take a look at the dataset that is used to train this network. We use two different approaches for generating the ground truth alpha maps for supervision. The first one uses a technique called ratio matting, proposed by Deberbeck et al. The main idea is that we place a gray board behind the subject, and for the one of the frames in the sequence, we illuminate the board, but not the subject. So the subject creates their own silhouette, which we can use to extract the alpha channel, mostly using the inverse of the ratio between these two images that we saw here on the left slide. However, this is only possible for a couple of frontal camera viewpoints in the light stage. Additionally, to generate this pair of aligned images, we have to perform dense flow estimation, aligning the alpha matte together with the fully lit image, also known as the tracking frame. Again, this is only for the two frontal views of the light stage. For the other views, the background behind the subject may be cluttered with lights, cameras, and cabling, as you can see here in this slide. For this, we train a neural network specifically for the task of generating ground truth alpha mattes for these other viewpoints. This is somewhat similar to our main deep matting model, except this time we provide as an input a clean plate of the background. And of course, we could train this network using the ratio matting dataset obtained from the two frontal cameras. Here we can see more results for a different subject of our test set from many different viewpoints at the light stage and the predicted alpha mattes. Now, let's look at the losses we use to train the deep matting module in total relighting. First, we use a sparse cross-entropy loss between the refined dry map and the ground truth dry map. In this case, the ground truth dry map is generated by eroding and dilating the ground truth alpha matte with a small kernel for 1-2 iterations, which produces a tight dry map around the ground truth alpha matte. Then we have an annual loss on the foreground image, alpha matte, and reconstructed color image, what is usually known as the compositional loss. Additionally, we have a pyramid Laplacian loss on the alpha matte. This multi-scale loss on the predicted alpha matte takes the difference between two Laplacian pyramid representations, accounting from local and global differences. Now, let's look at some results. In this figure, we saw the estimated alpha mattes for in the wild images. We can see that our method is able to recover fine detail and accurate alpha mattes, even when the user is in front of a complex background. We also perform a comparison against some pre-trained state-of-the-art matting models. Note here how the proposed matting model better generalizes on in-the-wild images when compared with these state-of-the-art pre-trained models that were only trained using the Adobe 1K and the alphamatting.com datasets. Here we can see more results and comparisons on in-the-wild images. Additionally, as a byproduct of our proposed approach, we analyze the importance of data augmentation when training an alpha matting estimation model. In particular, we assess the effect of using accurate relighting when generating a large dataset of realistic composited images. In this figure, we can see some qualitative results on our evaluation set, training our model using different dataset configurations. First, training our deep matting module only on fully lit images. Secondly, training it on color harmonized images. And finally, training on realistically relighted images using the light stage. We can clearly see the improvements of our model being trained on the Relighting dataset. For more details about these ablation studies, please check out our paper. Now, let's switch to the Relighting module. The design of the deep Relighting module includes several unit architectures in a chain, designed to assist in relighting by supervising on intrinsic image decomposition. A first network estimates the subject's geometry, which is represented as a per pixel surface normal. A next network estimates the subject's diffuse albedo, which is essentially a fully lit portrait of the subject. Recent prior work on relighting has shown that supervising network training with these intrinsic components can improve relighting results, so we leverage this finding in our approach. The lower part of the diagram, however, shows one of the key new contributions of our work, which shows how exactly we supply the input lighting environments to the relighting network. The idea is based on the diffuse and specular convolution operations, and this is borrowed from previous works on real-time computer graphics. Basically, if you convolve the HDR lighting environment with cosine lofts representing either a Lambertian or a specular from VRDF, you can create this light map representation by indexing into the convolved panoramas using the surface normals. In gaming, this was implemented as a texture lookup using either reflection vectors or surface normals. In our case, we use the built-in TensorFlow image resampler. These light maps are essentially a way to represent the input HDR lighting environment in a way that is pixel aligned to the input image. Why is this important? Because unit type architectures prefer pixel aligned inputs. Previous work in lighting estimation, including the single image portrait relighting work that I introduced earlier, simply supply the HDRI illumination to the network at the bottleneck of the encoder-decoder architecture. Thus, the network had to learn a complex mapping from panorama pixels to portrait pixels, which we avoid entirely using this classic real-time rendering technique. To visualize why these light maps are helpful, we can look at the following intermediate images. For a given input portrait, A, we can predict the albedo, B, and surface normals, E. We can then use the diffuse convolved lighting environment and the normals to create a diffuse light map, shown in C, which is the subject's appearance if they had a perfectly Lambertian VRDF. If you multiply together B, albedo, and C, the diffuse light map, you can arrive at a diffuse reflectance image of the subject, which we saw in D, which also has the correct color, directionality, and overall diffuse shading, but it misses specular highlights and more complex shading effects. The specular light maps, as in F, provide the final relighting network with a hint about the location of the specularities in the final or in the new Relight portrait. Finally, in H, you can see our final neural rendering result. So the main idea is that this is a much less difficult learning task compared with just image in and image out from previous works. In our shading network, which does most of the neural rendering work, we supply the albedo map, the input foreground, and multiple specular light maps compute with different Phong exponents, which mostly control the strength of the specular highlights. All these images are passed as an input to a first network that we call specular net. The idea here is that we learn a per pixel specular light map, which can pull pixels from each of the candidate specular light maps. The final specular light map, the albedo, and the diffuse light map are provided to the neural rendering network to estimate the final Relight foreground image. Now, let's take a look at the dataset that is used to train these networks. To train these modules, we use a large dataset captured at the light stage. This light stage dataset includes images of about 70 people from about 60 camera viewpoints and lit by about 300 lighting directions. Basically, from our OLED images left, we can generate the target Relight images, and with the alpha math, we can composite the subjects into backgrounds extracted from the HDR panoramas, as we can see on the right. Additionally, we also get an image of the subject under the full sphere of lighting, which works as a proxy for the albedo. And we use the one light at a time images to perform photometric stereo, allowing us to recover ground truth accurate per pixel photometric normals. In this slide, we can also see the estimated alpha mask, corresponding trimap, foreground color, and final composited image on a high-resolution HDR map. Finally, we can look at the loss terms for the relighting module. All of these are compared with the ground truth that we just saw. We have an N1 loss on the geometry image, albedo, and Relight image. We also have a BGG loss on the albedo and Relight images, using features extracted from the images with a pre-trained BGG network. We also have an N1 loss on the Relight images, after first weighting them using the specular reflection map. The rationale behind this is that we can train the network to focus in particular regions that are likely to contain specular reflections, which are challenging for the neural network to synthesize. This is essentially an attention mechanism for the network. We also have adversarial losses for the phase region only, for the albedo image and for the Relight image. For the Relight phase image discriminator, we supply a phase crop of the specular reflection map to act as an attention mechanism for the discriminator, as I mentioned before. Now, let's look at the results. In this slide, we saw the input portraits on the left. These are in the wild images, so we don't have ground truth light stage data for any of these subjects. And now, we use a different few lighting environments to relight these three subjects. From left to right, we are basically rotating the lighting environment around the subject and generating the final composited and relight images. The idea here is that a photographer can generate a new set of compelling portrait images from input in the wild ones. I also want to particularly point out a few features from this method. First, the network successfully removed specular highlights, and you can see this in particular in the top and bottom rows of the images. Additionally, the network also successfully adds specular highlights, and this is apparent in most of the images, but particularly for the second row. Here we can see a few more subjects, this time showing the rotating lighting environment on the top of the part of the figure. We also compare the relighting module of our framework with the two most recent state-of-the-art approaches for single image portrait relighting, Sun et al. 2019 and Wang et al. From 2020. Both methods require a single RGB input image and target HDR lighting environment as input, as in our approach. However, each of them uses a different lighting representation. As we can see in this image, our method generates superior results on these evaluation subjects. Additionally, quantitative experiments carried out in this work show that even when training some of these models on our latest stage dataset, our lighting representation still allows for more accurately rendered specular highlights while also preserving sharp details in the final image. These experiments highlight that only relying on high-quality training data is not sufficient to get state-of-the-art results, and that the light representation is a crucial component of our framework and contributions. In this figure, we saw qualitative comparisons between the proposed approach and previous state-of-the-art relighting methods using in the wild portraits. Our approach is able to accurately relight subjects of different skin tones, whereas other techniques fail. Similarly happens when synthesizing specular highlights and hard shadows. Although our network was trained on single images, so not temporal information, we also generated results running our network for each frame of a video. And a few results are shown here. In particular, we saw per frame alpha max, albedo, and some relighting results, as we can see here. Here, additionally, we saw some applications of our work, some additional applications of our work. So in this setting, what we are doing is to estimate the lighting from the input images at the left, using a previous work called Deep Light from Legendre et al. And then relighting the subjects on the top row to composite them into the original scenes below, using the estimated lighting from the input images, from the input background images. So no HDR map is involved here. Another application of our system is as a data augmentation module for training models for other computer vision tasks, such as face, object detection, image classification, segmentation, etc. We have the ability to generate a lot of dataset variability given in the wild input portraits. But now, let's take a look at some of the limitations of the current method. First, you may have noticed that we don't always estimate the correct albedo for clothing regions. You can see this especially on the subject on the right, where the albedo inference network identifies those dark parts of the shirt as being caused by shading rather than surface reflectance. Additionally, our relighting network is not able to generate the specular highlights that you may want to see in the eye region. And we would like to fix this, as we think that eye reflections and specularities are really critical for compelling portraits. Finally, when applied to video sequences, our approach may exhibit some temporal inconsistencies and flicker in the alpha matte prediction, as you may have seen before in the video. With this, I would like to conclude my talk. So thanks for your attention, and for any questions, please feel free to reach out.
Hey everyone, I'm Prathul Srinivasan, and I'll be talking about recovering relightable neural radiance field representations. Before we get started, just a quick intro about myself. I recently completed my PhD at UC Berkeley, where I was co-advised by Ren Ung and Ravi Ramamurthy. Since then, I've been working as a research scientist at Google Research, where I'm a member of David Salazin's organization. Specifically, I'm part of a team led by John Barron, and I work with Ben Mildenhall and Peter Edman on various problems related to inverse rendering, 3D object and scene capture, and in particular, neural radiance fields, or NeRFs. Okay, so hopefully you're not too tired of hearing about neural radiance fields and view synthesis from earlier talks in this course, so I'll keep my review pretty brief. Neural radiance fields, or NeRF, is a technique for view synthesis. The overall idea is that we start with the observed images of some object or scene, along with the corresponding camera parameters, and we recover a neural radiance field, which is a 3D representation of the scene I'll talk about in a second. That's able to render photorealistic images of the scene from novel unobserved viewpoints, like here we're seeing of this drum set. So to recover a NeRF from observed images, we first shoot out rays through pixels corresponding to the images that we've observed, and then we sample a bunch of points along each ray, like we're showing in black on the left side of the figure here. Then, we pass each of these points as an input to a multilayer perceptron, or MLP, shown as f with parameters omega here, and for each of these points, the MLP returns an estimate of the volumetric density at that continuous 3D coordinate, and the estimated color of radiance that's emitted by particles at that location along the viewing direction that's corresponding to the ray. So next, we accumulate all of these values along the ray into a single estimated pixel color using just standard volume rendering techniques. And to train the network, we simply optimize its parameters, omega, to minimize the square difference between the actual observed pixel colors and the pixel colors that we've estimated using the network's outputs. And by minimizing this re-rendering loss across all observed camera pixels, the network's encouraged to represent the scene by allocating high volume density to the 3 locations where surfaces actually exist in the volume, right? This is just the multi-view consistency queue. And the network's also going to be encouraged to assign the correct view-dependent colors to these locations, such that they can re-render the observed images. So after this optimization, we're able to use the trained NeRF to render really nice photorealistic views of the objects and scenes from novel viewpoints that we had not observed in the training data. And these results are really cool and convincing. Let's keep in mind that a recovered NeRF is very different from a 3D asset that you can use in the standard graphics pipeline. So one of the most important functionalities that I want to talk about today that we're missing is the ability to simulate what these scenes and objects would look like under different lighting conditions. So today, I want to talk about some of our work towards answering this question. Can we use a similar neural inverse volume rendering approach that was shown to be really effective for view synthesis to recover relightable 3D representations of objects that bring us closer to a representation that we can use in actual graphics pipelines, like for games and film? So we can think of NeRF as representing a scene as a continuous volume of particles that emit light. And rendering a ray that passes through a NeRF representation is pretty simple. Right, we just sample points along the ray, and the final color is a sum of light that's emitted by particles at each point, multiplied by how much that point is blocked by the closer samples. And NeRF works well for rendering the same scene from novel viewpoints, but it doesn't really give us a way to simulate how any point's appearance will change with new lighting conditions. And to enable relighting, we first need to replace NeRF's model of all points being light emitters with a model where all points have surface normals and a reflectance function that can describe how the particles reflect incoming light. Then we can simulate how the light from external sources, like these colorful light bulbs here, is attenuated and reflected by the particles in the scene. And so this basic idea was like the key idea behind the really cool neural reflectance fields work that Zheshang talked about earlier today. In a neural reflectance field, the network outputs a surface normal direction and BRDF parameters at each point in the volume. So let's think about how we'd compute the color of this camera ray for a neural reflectance field, only considering direct lighting from these point light sources, again, the color of the light bulbs. So when I say direct illumination, I mean that we're considering the effects of emitted light that's just reflected by particles along the camera ray back toward the camera. So we first have to query the network for the volume density at each point along the camera ray to figure out how much each of these points is blocked by the closer points. Then, for each of the points, we must compute the visibility between that point and each light source by densely querying the network for volume density along each light ray. So keep in mind that each of these dots represents a full evaluation of a fully connected neural network, and that we have to do this procedure for every ray in the training batch, for roughly maybe 1 million training iterations per scene. So simulating direct lighting with this brute force visibility sampling like this would be way, way too slow during training. And so a really cool insight from the neural reflectance fields work is that if the lighting is controlled and the object is only illuminated by a single light source, and that light source is co-located with the camera, then we're actually already computing all the volume densities that we need to estimate the light visibility with the queries that we were already doing along the ray to render each pixel. So the training is really no slower than in standard NeRF. And so while this capture setup can recover really impressive relightable models, as Zhang showed earlier, it prohibits us from trying to recover relightable models under more general lighting conditions where we have many more light sources. So the question I've been interested in is, how can we simulate more complex light transport in a similar neural volumetric inverse rendering framework in a way that's still tractable during training? And so I, along with my teammates and some collaborators at Google Research, Berkeley, and MIT, investigated this question in a paper that's going to appear at CVPR later this year, or maybe in a month, called NeRF, or Neural Reflectance and Visibility Fields. So as we just saw, it quickly becomes impossible to do brute force visibility training within a training loop for more than a single point light source, which is unfortunate because it limits us to only using images captured in controlled environments. So instead, to get around this problem, we propose to approximate the visibility computations during training with a neural network that's going to take in a 3D point and direction and output the visibility of the surrounding environment along the corresponding ray. So at each of these points we're visualizing along the camera ray, we can evaluate the network to get the visibility from that point to the environment lighting in any direction with a single network query instead of requiring a dense set of queries along the light ray. But how do we efficiently supervise this visibility network while we're training? Well, we can make use of the same observation from neural visibility fields, neural reflectance fields. So during training, we already have to query the MLP for the volume density at densely sampled points along the camera rays. So these values are exactly what we need to compute the light source visibility for light sources that are coming from the positive or negative view direction of this camera ray. So for each training ray, we have the data to supervise the visibility network to predict the correct visibility in either of these two directions. And if we consider that the geometry is actually changing pretty slowly during training, and that we're sampling rays that view the scene content from all directions, we're able to actually train this visibility network alongside the network that represents the scene geometry, and this encourages the predicted visibility to be consistent with the current geometry at any point during training. Okay, so now we've come up with an efficient approximation for direct lighting visibility that we can use during training. But what about indirect illumination? How can we simulate that? Simulating indirect illumination can be really important for recovering accurate 3D representations, since indirect lighting can have a really significant impact on the appearance we actually observe in the images. So we really need to take that into account when solving this inverse problem. So here's a fun example, right? This is like what Shrek looks like with just direct environment illumination. And here's what it looks like if you try to model the indirect illumination that's bouncing off his body in the ground. And the main point I'm trying to illustrate here is that since indirect illumination has such a significant impact on the appearance, if we don't have a way to model the indirect illumination during training while we're trying to recover our 3D representations, we're going to end up estimating incorrect geometry and incorrect reflectance parameters in order to try to simulate this difference in appearance. So unfortunately, simulating indirect illumination with this brute force visibility computation strategy is even more daunting, because indirect lighting can arrive at a scene point from all directions. And so repeatedly querying a network for the densities along all possible indirect paths would be way, way too prohibitive in a training loop. So we need to introduce another approximation to make this more tractable. So what we're going to do is that we're going to additionally train the visibility network to predict the expected termination depth for a ray that's leaving a 3D location in a given direction. And so this is implicitly making an assumption that since we're actually trying to recover a model of an object with opaque surfaces, then the one bounce indirect light arriving from any direction is actually just largely due to light bouncing off a single other point in the scene. So then we can estimate the one bounce indirect illumination at a point arriving from any direction by computing the direct illumination shading of the corresponding predicted termination point using the visibility approximation from before. So this diagram is illustrating how the indirect lighting is computed for the middle point along this camera array. We're sampling random directions on the upper hemisphere of this point and querying the approximate termination depth in each of these directions. And then we shade the corresponding these termination points using the direct lighting visibility estimate from before. But how do we supervise the network to predict the expected ray termination depth? So actually we can use the same trick from before and note that by evaluating the volume density along each of these camera rays during training, we're actually computing the values we need to compute the expected termination depth of a ray that's cast towards a positive or negative view directions from any of these points that we've sampled along the ray. Right? We can essentially accumulate the opacity in either direction for each of the points on the ray, and there's some efficient ways we can do that. Cool. So now let's take a look at some results and see what these neural approximations I've been talking about look like in experiments. So in this experiment, we started with 150 images of a synthetic scene of hot dogs on a plate. So the scene is illuminated by a full spherical area light, in addition to a point light that moves to a different location for each rendered image. So similarly to NeRF, we're just going to train this NeRF representation to minimize the L2 error of re-rendering these training images using the given camera positions and given lighting conditions. And we're not going to impose any priors on any of the represented functions we're talking about. So our learned approximations let us simulate pretty complex volumetric light transport at each step within the training loop. And that in turn allows us to recover a relightable 3D scene representation using only those images as inputs. So for any continuous position in space, NeRF is going to represent the surface normal. And in our case, we're representing the surface normal as the negative normalized gradient of the MLP's predicted volume density at that location. And we're also representing the BRDF at any point, which we parameterize by a diffuse albedo and specular roughness, and we use a standard microfacet BRDF model. And on the bottom row, we're visualizing our learned visibility approximation, and we're visualizing this as a shadow map for a smoothly moving point light position. And so this lets us inspect this approximation gap between our network approximated visibility that we use during training and the actual visibility that we use during testing, which will look more like the crisp hard shadows that we're seeing in our final renderings on the left. So we can see that this visibility approximation that we use during training is like pretty reasonable, right? The shadow moves accordingly to how you would expect, but it's not as crisp. And so there is like an approximation gap, right? So this approximation is definitely not perfect, and we're hoping it's good enough for training. Finally, we can also visualize the renderings with just direct lighting and just indirect illumination. So let's take a closer look at the NeRF representation for 3D points in a scene, like this one marked in cyan. So as we move the 3D point in space, like kind of along this hot dog scene, we can see that the predicted visibility that the rays intersecting the hot dogs or the plates are correctly predicted to be blocked. Right, we're seeing the predicted visibility change as this point moves over the plate and then moves around the hot dog. And we can also see that the predicted reflectance is going to recover the specular lobes of the plate material, as well as the changing albedo of the hot dog and ketchup, right? So here's another example where we can see the predicted visibility account for the blocking effect of the armadillo as this 3D location that we're tracking with the blue square moves up the armadillo's leg. And so let's take a closer look at the effect of indirect illumination in our model. And we can do this by toggling between renderings from our recovered NeRF model with and without the indirect illumination contribution. And we can see that NeRF is able to simulate realistic global illumination effects that are caused by NeRF reflections, like the extra lighting around the base of the hot dog, and this like the kind of glow that we see inside the cab of the Lego bulldozer, and even the reflected light from the ground and the armadillo's hands onto the shadowed face or the front body parts of the armadillo. Finally, since NeRF decomposes the scene into underlying geometry and reflectance properties, it's pretty easy to edit a recovered NeRF model. And for example, we can edit the material of the recovered armadillo model to make it more metallic. We can edit this Lego model's albedo and material to make it kind of look like it's made of marble. And we can turn these hot dogs into gold by manipulating both the BRDFs and albedo. So I think that this line of work is just beginning, and there's tons of really interesting open questions for us as a community to answer and investigate before we can expect to really easily recover high-quality, relightable neural volumetric NeRF-like models by simulating complex light transport from general lighting environments. And keep in mind that doing this kind of simulation during training is what's the really hard and expensive part. So one of the more practical roadblocks that we face in this project is how can we manage the artifacts that are introduced by the positional encoding that we're using. So Ben Mildenhall earlier today talked a little bit about positional encoding and coordinate-based MLPs. And so in NeRF, we're using multiple coordinate-based MLPs to represent these different functions that all interact with each other to produce a rendering. So when we look at some of the functions represented in NeRF, and in this visualization, particularly look at the roughness and the shadow maps here, the visibility, we can see pretty strong axis-aligned artifacts in the represented functions. And I think these artifacts are likely due to the extra high frequencies that are introduced by positional encoding that we use in coordinate-based MLPs. So it'd be really useful to have better ways of maybe regularizing the smoothness of these coordinate-based MLPs to avoid such artifacts. Another question I think is really interesting is how do we model scattering during training? Right, so even if we know that we're trying to recover representation of an object with opaque surfaces, there could be an optimization benefits in considering scattering functions that are not purely reflective, like BRDFs during training. And then with the expectation that they'll end up as a purely reflective model at the end of optimization. Right, so conceptually, you can kind of think this is similar to how we model geometry as semi-transparent and volumetric, kind of fuzzy geometry while we train NeRF, even though we expect the geometry to harden up into surfaces by the end of optimizing a NeRF. Right, so in NeRF, we have this intuition that using softer representations that don't restrict our geometry to surfaces results in better behaved optimization. And maybe we can carry some of this intuition into the material recovery as well, and use functions that allow more general scattering while we're training for better optimization purposes. Another really interesting question, I think, is how does the slack between our network predicted visibility approximation and the actual true visibility end up affecting optimization? Right, so here we're jointly training this approximation with samples of the true visibility from the current state of the geometry during training. So we're treating the visibility network as kind of a soft cache, right? So it represents some state of what we think the visibility is for the geometry, and if the geometry changes, we make some estimates of some points of this visibility function and try to update the network to account for that. But there's no guarantee that this network's approximation is actually equal to the actual integral of volume density for the current state of geometry. And I'm thinking this is likely cause of errors that we see in the final recovered representations, since the geometry and material parameters essentially have to be less accurate to compensate for the errors in visibility during training. And so I think one really potentially really fruitful direction could be to use the idea of automatic integration, which constructs two networks with tide weights, such that one is guaranteed to represent the integral of the other. And I think Gordon probably talked about this today. And we could have the integral network represent the visibility, so that the visibility network is actually exactly consistent with the geometry at any point during training. And I think the AutoInt is a really nice and elegant idea that could be exactly what we want in this scenario, where the most painful part of doing volumetric path tracing within a training loop is computing the visibility integrals to figure out how much light reaches each point. Cool, yeah, that's all. Thanks.
All right, so hi everyone. My name is Michelle Guo. I'm from Stanford University. And today I'll be talking about compositional scene representations. So as you probably all know, and probably previous talks in this course have already covered, NeRF is this recent work that is able to demonstrate really high fidelity renderings on the task of novel view synthesis. And it really works really great for static scenes. So scenes where things are not moving, the lights are not moving, we can represent a static scene very well with a single NeRF. But the challenge is, how do we deal with dynamic scenes with NeRF? And naively, what we could do is train one NeRF for every single frame in a video, for instance. So each time the object moves a little bit, we can retrain a NeRF. And That way we can have a NeRF for each frame and then represent the entire video. But that is really inefficient, and that kind of brings me to the work I'll be talking about today, which is object-centric neural scene rendering. And the goal of this work is to address the limitation I just described. How can we represent dynamic scenes without having to retrain every single frame? And this is joint work with Alireza Fathi, Jiajun Wu, and Thomas Funkhauser. And the idea of this work is that given some scene parameters, any scene parameters of lighting, camera, and rotation and translational parameters of each object, and then given a pre-trained library of objects, we want to be able to compose different scenes using our library of objects. So as you can see here, this scene is simply a composition of the objects I'm showing here in this object library. But then also we want to be able to move the light in the scene without having to retrain, as well as move the camera and also move the objects, again, without retraining, but purely just reusing this kind of pre-trained library of objects. So in order to describe how this works, I'm going to break down this talk into two main components. First, I'll talk about object level light transport. So this is about modeling how light transports for each object. And then once we've learned a model for each object, our goal is to then figure out a way to compose these different objects into a scene. Okay, so before I get into the details of our method, it could be helpful to quickly review the rendering equation. And so what we're doing is we're computing the radiance of a single ray with origin x0 and direction omega O. And the way we compute the radiance is just an integral from some near and far bounds over these terms, which includes the accumulated transmittance along the ray up until this sample t, and then the density at that sample, and then finally the amount of light that is scattered at that point in the direction omega O. And as a reminder, this accumulated transmittance term is defined as the following above. And so how is this LS scattering function defined? It's defined as the following equation, where we're taking an integral over all incoming directions over a 2D sphere. And for each incoming direction omega L, we're computing the radiance at the point x in direction omega L multiplied by the fraction of light scattered at x from omega L into omega O. And you can see here that the radiance defined here is recursive. You can compute this with the first equation above. And just as a side note, NeRF also follows this rendering equation, except that they encode this LS term directly. So they are not explicitly computing the second equation. But we do consider this second equation, or this more general form of rendering equation in general, because we want to be able to deal with the explicit light paths that are transporting in a scene. And so to render a single object, we can first consider a simpler case of the second equation, where we actually only have, we assume we just have a single light source, so no more integration, just these two terms here. And then we can maybe also further assume that we only have, the light source is only a radius of 1, so that L term goes away and we only are left here with FP. And so taking these equations together, we can see that our unknowns are now just the volumetric density at a given sample, as well as the amount of the fraction of light scattered, this FP term here. And so to obtain those values, what we do is we learn the 7D object-centric neural scattering function, or OSF for short. And what this neural network does is that it takes in the spatial location, incoming light direction, as well as outgoing light direction, feeds it into an MLP network, and outputs the fraction of light scattered, as well as the volumetric density. So together, this is the whole OSF network that we represent each object by, and just like NeRF, we apply positional encoding to the inputs. So that described the object level light transport. And now I'll talk a little bit more about how we actually take those individually learned object models and compose them together to render a scene. All right, now let's go back to our original render equation, which is shown here. And we can actually now relax our assumption from before that we only have a single incoming light direction. But instead, what we want to do is we want to integrate over all incoming light directions over the 2D sphere. So as you can see here, I've drawn a single ray with different samples, and for each sample, we consider multiple different incoming light directions, and that corresponds to the second equation here. And what this gives us is a method for volumetric path tracing. So given a camera with some primary rays, we can essentially compute the radiance for those primary rays to obtain the final pixel values in the image we want to render. But how do we actually obtain the radiance of those individual primary rays? Is that we have to consider these different types of secondary rays, including direct illumination from light sources to objects in the scene, as well as shadows rays. So this gives us a method of testing whether a point with a ray sent back to a light source, if it's being occluded by other objects. And then finally, we can also consider indirect illumination effects, where different objects are indirectly illuminating each other. And so these are the different types of rays altogether that we consider in our system. So I'll illustrate our method with an example for shadow rays. So let's say that we have a scene specification where we have, let's say, a cube here with like a ground plane here, and our goal is to render as an image of the scene. And let's say that we deal with just one primary ray from the camera for now. And what we do is we can sample along this primary ray, and for each sample, we can shoot a shadow ray to the point light source. And we can do this for every single point along the primary ray. And so for each shadow ray, what we do is we, again, recursively sample points along this shadow ray, and then we can compute the densities along this ray using our OSF model that is trained. And given these densities, we can then compute the transmittance along this ray, which is simply the cumulative product of 1 minus the densities. So this tells us, as a function of the distance along the ray, how much light actually reaches a certain point along the ray. And you can see that as the ray kind of reaches beyond the cube, it gets dark, and that's because the cube itself is occluding light from traveling to these later points along the ray. And so given that transmittance computation, and if we do that for all of the different shadow rays, each point will then have its own computed transmittance, and we can essentially multiply the original RGB color of each sample by the transmittance that we computed from the shadow rays. And so that previous example was assuming that we had a point light source, or a light source that's really, really tiny. But if we want to consider a larger area, like an area light, all we have to do is to just sample multiple points on the light source and essentially send multiple shadow rays. This will kind of give us a sampling over different points on the light source. Okay, so that was just a little diagram of how sending secondary rays for computing shadows works. Now I'm going to explain how we can make our method more efficient, because if we're going to be sampling samples along each array multiple times, and then each of those samples also has its own n samples, then it could quickly become very inefficient. And so what we do is we adopt a sparse ray box intersection approach. So given a scene and a camera, the scene has 3 objects here that are represented by 3 OSF networks. We can render the scene by sending primary rays into the scene, but if the primary rays do not intersect with our objects, then we actually can just ignore them. And for the rays that do intersect, all we have to do is sample between the intersection points as our near and far bounds. And for secondary rays, what we could do is, given, let's say this single ray, for example, how do we compute secondary rays? Well, so for each point, we can send a secondary ray to the light source. And for the rays that don't intersect with any objects, we can again discard them. And again, only sample within the intersection bounds. Cool, so now we'll go more into the results. So first I want to show results on a single object, but how it's able to generalize to novel illumination. And so the first row here is the ground truth, the second row is our method, and the third row is a variant of NeRF. And as you can see, our model is able to match the ground truth well, versus NeRF has trouble getting the appearances, the specularities of the Ottoman. It's showing weird shadows on these objects, and that's because it's not dependent on the incoming light direction. The next result that we want to show is on scene composition. So how do you kind of render multiple objects in a scene, and how does that compare to the ground truth? So the first column is our method, the last column is ground truth, and the second and third columns are different variants of the NeRF baseline as well. And as you can see, our method is able to capture the appearances, shadows of the different objects very well, versus the second and third rows definitely are not able to show consistent appearances or shadowing, especially if you look at, for example, the chair is just not consistent. Here's more results. Same columns, but this time we're moving the camera around. And here we have results on a moving light. And you can see that our method is able to recover shadows very well, versus, the vanilla NeRF method does not even account for shadows being cast between objects. Finally, we want to show some real-world results. And so what we did was we first trained OSFs on individual objects that are captured in the real world. These are objects from the Neural Reflectance Fields paper this year, and these are just different objects that were collected in a darkroom. And here are results on composing those individually learned objects into scenes. So here we have the effect of moving objects. You can see that as the objects are moving around, the shadows are able to kind of cast on each other from the pony onto the other two objects accurately. In the middle is what it looks like if you move the camera around, and then finally this last video is what it looks like when you move the light. And you might notice that when objects are casted by a shadow, by another object, that the objects are still not completely dark, and that's because of our implementation or inclusion of secondary rays that account for indirect illumination. And so the light from the ground is illuminating the objects, and that's why the objects don't look completely black. Finally, we show results on inserting these three objects into real-world scenes. So these two are real-world outdoor scenes that were from the NeRF paper, and we show that we're able to insert additional real-world objects into these real-world scenes. So it really demonstrates the power of being able to really only train OSFs once for the lifetime of all of these different objects, but being able to reuse them infinitely many times to create a variety of different scenes. Cool, so that's all I had for today. If you're interested in learning more, you can check out our paper on arXiv called Object-Centric Neural Scene Rendering. Thanks.
Hello, and welcome to this talk. My name is Edgar Tretschke, and I'm a PhD student at the Max Planck Institute for Informatics. In this talk, I want to give an overview over a number of recent papers that extend neural radiance fields to general dynamic scenes. The problem we want to look at takes as input a monocular RGB video of a general dynamic scene and is not restricted to faces or human bodies, as can be seen with the stick in this example. We then want to get a 4D reconstruction of that scene, namely the geometry, appearance, and deformations. This reconstruction then allows us to synthesize novel views in space and time. Ideally, we want these novel views to be consistent across those dimensions, as you can see in this example. So what's difficult about this problem? Well, we need to accumulate the geometry and appearance information across time, but this leads to ambiguities. Static scenes already exhibit ambiguities between geometry and appearance. For example, we could place a flat plane in front of each camera instead of learning a representation that is actually, 3D. But with dynamic scenes, we now also encounter geometry changes like motions and deformations, and appearance changes in the lighting, for example, in the form of shadows or in the material. All of these can again be exploited by the optimization to avoid reconstructing a meaningful 3D scene across time, since we only have a single input view per time step. So this problem is even more under constraint than static reconstruction. Because of that, we need to impose priors on the deformation modeling. So as I already hinted at, since we observe only a single view per time step, the deformation model needs to handle the currently hidden geometry, ideally, reasonably well, in order for novel view synthesis to give reasonable results. In addition, when parametrizing deformations, we also need to be able to, for example, introduce discontinuities into the parametrization in order to handle topology changes. So there's already some related work, but these works focus on closely related problem settings. So in general dynamic reconstruction, these works, for example, differ because they rely on depth, they only model hard surfaces, they assume a template, or they, are image-based. There are also some closely related neural representations that, in addition to these differences, for example, also differ by using multi-view input or 3D supervision. And then late last year, we saw a wave of NeRF-based works coming out that made significant progress over previous attempts at a full problem setting. So these works mostly consider real monocular videos as input. Here we have NeRFs, NeRFflow, NRNeRF, NSFF, and VideoNeRF. There are also a couple of other works that use slightly different input settings, namely DyNeRF, which uses multi-view video, or synthetic videos like dNeRF. So, how can we add deformations to NeRF? Let's start by looking at neural radiance fields. They represent a 3D scene as a function that maps any 3D point to its opacity and color. This mapping is implemented by an MLP. Given a radiance field, we can specify a virtual camera and trace rays from it. We then employ volumetric rendering by sampling the radiance field along each ray and integrating the samples to obtain the final image. This formulation, however, only supports static scenes. If we want to capture dynamic scenes, we can additionally condition the radiance field on time. Unfortunately, this entangles the geometry and appearance with the deformation in a single MLP. To disentangle deformations from geometry and appearance, we can represent the dynamic scene using a static canonical radiance field and a separate deformation field. So we can use space warping to deform the underlying static canonical model. So let's consider the same dynamic scene at two different time steps. Since the space warping has deformed the volume, we can render the deformed state using straight rays. So that's the idea behind ray bending. But how do we realize that in practice? So we start with the straight rays. We then have to invert the space warping in order to access the geometry and appearance information in the canonical volume. That means that every point sampled along the straight ray needs to be mapped back to the canonical volume, thereby bending the ray. We can implement this as a ray bending function B that has the power to offset any point x prime along the ray to give a point x in the canonical volume. This function is conditioned on time, which allows it to map all time steps into the single same static volume. This ray bending is trained jointly with the canonical volume using a reconstruction similar to static NeRF and additional regularization on the deformations. So let's see how these two deformation models compare. We have time conditioning and we have ray bending. The crucial difference between both are correspondences or the temporal consistency that comes with them. In the case of time conditioning, the correspondences are more of a soft constraint. They're modeled by an auxiliary 3D scene flow and they can drift over time. This allows time-conditioned methods to reconstruct frames rather individually, since incorrect correspondences across time are not too problematic. Thus, these methods can empirically handle larger motion. We can see this here. So the input video on the left is rendered into novel views on the right. Note that the boy is rotating globally by 180 degrees. On the other hand, ray bending uses correspondences across time as a hard constraint. This is done via ray bending into a static canonical model. Thus, the correspondences cannot drift over time. That makes it unfortunately difficult to recover from a wrong estimation of large motion that might occur early during training. NeRF tries to use a curriculum to get around this. These methods empirically handle only smaller motion. Here we see a scene that exhibits motion that is at the most complicated end of what the current ray bending methods seem to be able to handle under monocular input. Another aspect are appearance changes like shadows or in the material. In the time conditioning framework, these are straightforward to model. The same holds for topology changes, as we can see again when looking at the bubbles in this novel view video. Note that the bubbles appear and disappear without too much issue. However, ray bending struggles with appearance changes since the canonical model that contains the appearance is independent of time. These methods also have difficulties with the discontinuities required for topology changes. So let's first take a closer look at time conditioning. How exactly can we share and regularize geometry and appearance across time? So NeRF flow uses several losses to handle static parts of the scene. But I want to focus on sharing information about dynamic objects across time. NeRF flow encourages the geometry, appearance, and key point positions in 3D to be consistent across time. It parameterizes the scene flow on which these losses are based by an MLP. This MLP outputs flow velocities, which a neural ODE then integrates in order to get the actual offset in between discrete time steps. But because of the neural ODE, the scene flow is continuous in time and invertible. I also want to point out that the scene flow is not used at test time. It is only used for regularization at training time. Next, we have NSFF. It handles static objects by having a second static NeRF that is not conditioned on time. When we then want to render, we merge the static and the dynamic NeRF. For dynamic objects, it also encourages consistency across time, but on the 2D rendering, not in 3D. It also regularizes the scene flow to be small, smooth, and sparse. These losses are again based on a learned scene flow, which is parameterized by an MLP. Except that this time, this MLP outputs the final offsets directly, which makes it discrete in time and difficult to invert exactly. And again, the scene flow is only used at test time, is not used at test time, only at training time. And finally, we have video NeRF, which does not constrain dynamic objects across time and instead implicitly assumes that they are always visible in the input frame. So after time conditioning, I want to talk a bit more about ray bending. The methods that use ray bending always use an MLP to parameterize the bending and not some classic representation. So what are the advantages and disadvantages of doing it that way? So just to recap, the MLP takes as input a 3D point at a time t and outputs an offset for that point. Because it's an MLP, it is flexible and expressive. It is also continuous in space and time and easily differentiable. That makes it easy to realize continuous natural deformation priors without any need to approximate them on a discrete representation like a mesh. So, for example, NeRFs can very naturally penalize the elasticity of dynamic objects via the singular values of the Jacobian of the ray bending. Similar to that, NeRF encourages rigidity by penalizing the divergence of the ray bending. On the left here, we can see a novel view rendering when training without a rigidity prior. And on the right, we see the same rendering when training with a rigidity prior. Furthermore, the differentiability makes it easy to determine the ray direction of the bend ray. This is necessary for view-dependent effects, where we use the ray direction at an instantaneous point along the bend ray, not along the straight ray. Another advantage is the inherent smoothness, which lets the MLP in-paint information on its own. It is also volumetric and can thus natively handle smoke or fluids. And finally, it leads to spatially and temporally consistent novel view renderings by construction. And if we use positional encoding for the input point, then we can slowly phase in higher frequencies over the course of training in order to have a natural coarse to fine strategy. There are, however, some disadvantages. So first off, it's a completely opaque parameterization, which makes it very difficult to edit or manipulate ray bending in a targeted manner. It is also fully entangled with no localization in space or time. And so we need to take care to prevent the loss of already learned information during training whenever we update the network weights. And since it is inherently continuous, topology changes are difficult to account for. And finally, MLPs are not trivial to invert exactly, although there are approaches that learn an inverse. So, lastly, I want to focus on novel views. The goal of our problem setting is to render novel views along a spatiotemporal camera trajectory that is significantly different from the input camera trajectory. Now, the issue is that at a certain time t, we are only given a single input view. And so only the geometry visible in that input frame is constrained by a data term. And so we need to impose priors on the hidden geometry that is not visible at that time in order to prevent artifacts from novel views. So For hidden static objects, NSFS uses a separate static NeRF as mentioned earlier. NeRFs optionally pre-computes 3D background points and encourages them to remain static. And NRNeRF tries to determine points that are static across the input frames where they are visible, and to then keep them static in frames where they were not visible. More interestingly, we also need to keep hidden dynamic objects in mind. NeRF flow encourages temporal smoothness for these points. NRNeRF encourages local rigidity along the 3 spatial dimensions. We can see the impact of that last loss here. On the left, we have the input frame. Next to it is a novel view rendering of NRNeRF. On the right, we have novel view renderings of 2 methods that were trained without constraints on hidden dynamic objects. And we can see that that leads to blur. So, to conclude, in this talk, I presented 2 classes of deformation models with complementary advantages. Time conditioning, which allows for larger motion, topology change, and material and light changes, and ray bending, which has hard correspondences across time and therefore temporal consistency by construction. Now, there's nothing new under the sun. What we have here are not 2 distinct classes. Instead, they are the extreme ends of a spectrum. Time conditioning treats every time step as a keyframe. Ray bending, on the other hand, uses, in a certain sense, only a single keyframe, namely the canonical model. We will hopefully see methods that fall somewhere in between in the future. We might also imagine a method that starts on the time conditioning end of the spectrum and anneals into a single keyframe over the course of training. So, some limitations that should be lifted are, of course, the standard limitations of static NeRF. Dynamic NeRFs are slow, they support only a limited scene size, there is no prior on how the scene looks beyond your observations, and so on. For dynamic NeRF in particular, a number of methods currently use auxiliary inputs like camera extrinsics and intrinsics, background 3D points, foreground segmentations in 2D, depth estimates, optical flow estimates, instance segmentations. It would be nice to reduce the reliance on these since they likely do not work well on difficult scenes. Okay, with that, I would like to close by mentioning 2 future directions, namely modeling physics, like the light or materials or the deformations, especially the impact of dynamic objects, and the ability to edit the representation. There were already a few examples in the discussed papers, for example, motion sculptures. We can also get some simple visual effects if we use foreground removal to simulate transparency. And we can exaggerate motion, as you can see here on the right. Okay, and with that, thank you very much for your attention.
Hi, my name is Steve Lombardi. I work at Facebook Reality Labs Pittsburgh, and I'm going to be talking about creating real-time, high-quality virtual humans. So in this talk, I'm going to cover a few different models for rendering humans from arbitrary viewpoints. These models take in a vector representing expression and camera pose parameters, and they output a realistic rendering. The expression code here is important for being able to drive and animate these avatars, but for this talk, I'm going to focus on the rendering aspects of these models. In other words, how do we create models that look as real and high fidelity as possible? So the methods I'm going to describe are all data-driven, so we need to be able to collect data so that we can train them. For input, what we use is a multi-view capture system to record multi-view video of a participant's face. For some of these models, we also need a little pre-processing on this data. In particular, we perform facial mesh tracking to acquire a corresponded 3D surface over the entire capture sequence. So once we collect this data, we're able to train some of these neural rendering models. In this talk, I'll describe 3 approaches that we've explored for generating realistic imagery. The first is deep appearance models, which works by dynamically decoding a mesh in a view-dependent texture. The next is neural volumes, which overcomes the limitations of the previous method, which is that it relies heavily on the existence and quality of the tracked mesh. Finally, we developed mixture of volumetric primitives, which tries to combine the benefits of the previous two methods and achieves the highest quality renderings. So first, let's talk about deep appearance models. The main insight into this method is that we can overcome the limitations of bad quality geometry with view-dependent texture maps. In deep appearance models, we do learning in 3D space by modeling a mesh and a view-dependent texture rather than directly modeling an output image. This is in contrast to many previous work, like StyleGAN, that operate in the image domain. These methods often have a hard time generating plausible results when smoothly changing camera poses. So why is this? Imagine that we want to interpolate multi-view images by simply blending them based on the viewpoint I want to look at them from. If we do that, we get a result that looks like this, which is not very compelling. This happens because we're trying to blend between different images, but the parts of the images don't line up, so when we're between cameras, we see a ghosting effect. If we want to train a network to smoothly interpolate in Viewpoint, we would need a very dense sampling of cameras. We can improve this approach a lot by using 3D information, like a mesh. If we project the input images onto the mesh to generate texture maps, we get this. So one thing that stands out here are these large regions of missing data, because those parts of the face are not seen by the camera. But beyond this, we can see that the features of the face all line up in the texture map. This effectively factors out an element of variation in the data, making the data easier to learn for our network. Therefore, we train a decoder that takes in an expression code and produces both the mesh vertices and the texture map. So the decoder has two branches, one that decodes the view-dependent texture map and the other that decodes all the mesh vertex positions. This method runs in real time because the entire network can be evaluated in less than 5 milliseconds on a modern GPU. To train this decoder, we construct a variational autoencoder. A variational autoencoder consists of an encoder and decoder pair with the objective of reconstructing the input data. We input the geometry and texture into the encoder, which produces a code, and we send that code through the decoder, and we want the output to be the same as the input. To train the system, we construct an L2 loss between the input and reconstructed mesh vertices and texture maps, and minimize it using SGD. This method generates very high quality renderings for the face. It's not without limitations, however. So in particular, notice how blurry the teeth are. So to understand these limitations a little better, let's take a closer look at the input and output data. Here we show an image from the capture system, the tracked mesh, and the resulting texture map. Watch the teeth, which are not explicitly tracked in the mesh as we cycle through different cameras. We can see that they move around in the texture map. This is because the 3D location of the mesh is not correct for the teeth. Now let's look at the output of the model from those same views. The sliding behavior is very difficult to model using convolutional autoencoders, so areas that are tracked well and don't slide much, like the cheeks, remain sharp, while the teeth are very blurry. We can allow the network to more easily model this sliding behavior by including a separate decoder branch that also produces a warp field. We apply the warp field to the decoded texture map to produce a final texture map. We found that adding a warp field works significantly better than simply increasing the number of channels in the decoder in terms of both quality and decoding speed. Here we show the template texture, which is the texture output by the decoder before warping, the 2D warp field, and the final warped texture. Notice how, without any direct supervision on the warp, the template learns to produce features that don't move. Here's another comparison of deep appearance models with and without warp. The warp enables the model to model high-frequency detail much better. Here's another comparison, without warp on the left and with warp on the right. Notice how the teeth are sharper and the eyes have sharper specularities. Can we just make the geometry better instead? So we attempted this but found that it can give mixed results. In particular, it can introduce high-frequency artifacts that can look worse than the blurry results. So notice the hard edges at the bottom of the upper teeth here. We also tried to improve the geometry during training by using differentiable mesh rasterization. And while it improves the fidelity of the geometry, soft materials like hair still look uncanny. With deep appearance models, we're able to produce really high quality renderings of the face, but we're generally limited by the mesh tracking quality. We can circumvent a lot of these problems with the warp field, but we still have problems with the occlusion boundary, which looks very unnatural. Volumetric rendering methods are appealing because they get rid of the need for input geometry and can better model non-planar surfaces than triangle meshes can. So the idea here is that rather than decoding a mesh and a texture, we can decode a volumetric field containing color and opacity. So for any 3D point in space, we can query this field to get a color and opacity value. An image can be rendered by ray marching through the volume, stepping along the ray, accumulating color and opacity to compute the final pixel color. Here I'm showing pseudocode for ray marching. A ray is evenly divided into steps, where we sample the volume and aggregate the samples into a final color and opacity. All these steps are differentiable, so the system can be trained end-to-end using only images and camera poses as input, by constructing an L2 loss between the reconstructed and captured images. Neural volumes is one such volumetric rendering technique. The main idea is to quickly decode a dynamic voxel grid from the expression code. We use a similar decoder from before, but we change the 2D convolutions to 3D convolutions. For voxel grid sizes up to 128 cubed, this voxel decoder runs in real time on modern GPUs. During ray marching, we sample the color and opacity using trilinear interpolation on the final voxel grid. So if we put this system together, we get a result like this. There's all these blocky artifacts because the voxel grid resolution of 128 cubed is relatively low. So why not just increase the voxel resolution? If we wanted to double the resolution to 256 cubed, we would need to perform roughly 8 times more operations, so this quickly becomes infeasible in terms of memory and decoding time. It would be better if we could make more of the resolution we had, for example by not modeling so many empty voxels, or making voxels smaller where there's more detail in the scene. To address this problem, we produced 2 volumes. One's a voxel grid containing color and opacity, and the other's a warp field. During ray marching, we first sample the warp field and use the result to tell us where to sample in the template volume. This allows the model to shrink voxels to increase their effective resolution and to minimize the voxels modeling empty space. This gives us the benefit of producing uniform voxel grids with fast GPU convolutions while eliminating the blocky artifacts. Importantly, no additional supervision is required for the warp field. It's trained only from the image reconstruction loss. Here on the left, I'm showing a rendering of the model using a warp field that produces a high-quality reconstruction without blocky artifacts. And on the right, I'm showing the template volume rendered directly. So you can see that it's kind of increased the amount of voxels used to represent some areas, and it's also factored out a lot of the motion from the scene, Notice how the head is almost totally fixed in this template volume. This is similar to what happened in the template texture map. This system can capture a lot of interesting phenomena that's difficult to model with non-volumetric methods. This mug full of dry ice is one of my favorite examples. Hair in particular is very challenging for 2D methods. This technique is able to capture the appearance of hair well without any explicit tracking data. We also have a larger capture system that we can use to capture full bodies, and we use the data from that system to create reconstructions of people. NeRFs produces compelling results on different scenes, especially those with transparent features or thin structures. It does have a few important limitations. In particular, many of the results appear blurry, especially compared to deep appearance models. Further, neural volumes waste a lot of time generating and ray marching voxels that only represent empty space, even with the warp field. One way to address the limitations of high-resolution detail is to simply combine deep appearance models with neural volumes. We can combine them by modifying the ray marching procedure to terminate ray marching when it hits the mesh. This gives high-resolution results on the face where the mesh is used, while also having the improved completeness of neural volumes. However, we're still stuck with low resolution outside the face and with a wasteful model. So to address these limitations, we created a mixture of volumetric primitives. One of the reasons why deep appearance models gave compelling results is that using a mesh and texture means all the modeling capacity is concentrated on or near the surface of the face. However, when the mesh is wrong, the results look bad. We can get around this problem by placing small volumes along the mesh. That way, the model can take advantage of the mesh when it's correct, but also deviate from this starting point if it's not correct. This allows us to get the benefit of more efficient mesh-based rendering while also improving the appearance of hair and improving the completeness of the model. Note, for example, how the mesh only goes down to the collarbone, but the volumetric primitives move downward to model the shoulders. In this work, we combine elements from the previous two decoders. First, we decode the color and opacity field, which is now a thin 3D slab as opposed to the 3D cube from neural volumes. We generate the mesh vertices like deep appearance models so that we can place primitives evenly distributed across the surface. Finally, we have an additional motion branch that outputs a 2D texture map with 9 channels that dictate the rotation, translation, and scaling of each primitive. The individual primitives are created by breaking the slab into small cubes and locating it according to the mesh position and motion offset. With multiple volumes in the scene, we need to slightly modify the ray marching procedure from before. What we do now is iterate over the set of primitives, checking whether the query point falls within the primitive, and if so, we sample and aggregate that point. This can become slow if the number of primitives is large, so we use a bounding volume hierarchy to compute a subset of primitives to check first. Here we show several examples of novel view synthesis renderings with this model. MVP is able to produce very high resolution over the entire model. Note that there are some artifacts on the shoulders as this region is often out of view of the camera. I've presented 3 methods that we've developed for generating high-quality models of human faces and bodies. Throughout the talk, we've seen that it's important to model real objects in 3D. Meshes are an effective way to do this, but volumetric methods can be better, especially when meshes are incorrect. Warping is a nice trick that works in both 2D and 3D to improve the model resolution and quality. We saw that improving the network's ability to model the data can give big improvements even when using an L2 loss function. We also saw that the volumetric methods can bring improved completeness to the model because it can model objects anywhere in space. It also provides a softer look around the occlusion boundaries that look better than mesh-based renderings. MVP is able to give high-resolution looking models, but it still requires a mesh as input. In the future, we hope to remove the need for this mesh and further improve the efficiency to run on mobile hardware. Thanks for listening.
Hello, everyone. I'm Rohit Pandey, and I'll be presenting some of the work that we've been doing on neural rendering for dynamic performance capture in the AR perception team at Google. So here's a brief outline of this talk. We'll talk about what is dynamic performance capture, some of its use cases. Then I'll quickly go into some of our previous work with Looking Good that was presented at SIGGRAPH Asia 2018, Simply Looking Good, also known as volumetric captures of humans with a single RGBD camera by semi-parametric learning. And then I'll get into some extensions like Looking Good++, and finally focus mostly on deep relightable textures, also known as deep relightables, which was presented at SIGGRAPH Asia 2020. Finally, I'll get into some in-the-wild applications and future directions for work like this. So what is dynamic performance capture? It involves capturing multiple depth and RGB streams for dynamic performer from multiple cameras. The depth and RGB streams are then fused into a textured mesh, which can then be rendered from any arbitrary viewpoint. The video here that you see is from the Relightable setup, which shows our latest capture setup and what it's capable of. These textured meshes can finally then be used for a variety of applications, including content for viewing in VR and AR, and also telepresence like communication applications, and also for data augmentation for machine learning methods. So a traditional capture and reconstruction pipeline, as I mentioned, would capture multiple depth and RGB streams from different viewpoints. The one we can see here is from the Relightables. These are then fused into a textured mesh with a particular UV parameterization. Now, this component tends to be common to a lot of these pipelines, but the Relightables goes a step further and actually captures gradient images, which enables us to use a handcrafted BRDF with a cosine lobe assumption to compute normal maps, gloss maps, and albedo maps. These can then be used to generate renderings that are relightable under any arbitrary HDRI lighting environments. So even though these capture pipelines are like this particular pipeline, the Relightables, goes pretty far in terms of quality and the renderings are fairly compelling, there are still some caveats of such a traditional geometric pipeline. So for example, there's lack of photorealism due to the handcrafted BRDF, which does not capture subsurface scattering and global illumination. There's missing geometry in certain areas, especially around hair on edges, and these pipelines have trouble recovering them. And the alpha mask computed from the rendered mesh also leads to more inaccuracies around edges. And compositing tends to show certain artifacts. So most of our work has been trying to focus on improving these traditional capture pipelines and kind of getting better quality out of them. So one of the works, the initial works that we did in this direction was Looking Good. At this point, our mesh looked significantly worse than the mesh in Relightables. However, the idea was fairly simple. Let's take the mesh, render it to the target viewpoint that we care about, and then re-render it using a deep architecture using an RGB image from a higher resolution witness camera as ground truth. So that was the basic idea. A neural rendering network predicted a mask, and it predicted the RGB output. There was a loss between the mask and the segmentation mask, and between the output and the ground truth image that came from a high resolution witness camera, as we called it. There were a bunch of losses that I won't get into details of that made this approach work well. Some key ones were the head loss and the saliency loss, which got us past some issues of our bad quality data at the time. So here you can see the results. The main thing to notice is that the input mesh itself was of terrible quality. And even though we noticed some issues with the output, it was quite decent given the quality of the actual inputs. The generalization to unseen people was a little bad at times. There was some memorization, but it was not terrible. But a lot of temporal flickering tended to carry on from the input to the output of the network. Similarly, we also had a setup that used the single camera only. So there was a single RGB and depth camera to the upper left of the person, and the rest was inpainted by the network. Some results on unseen people as well. Now, simply looking good, or as we called it, volumetric capture of humans with a single RGBD camera via semi-parametric learning, was a slightly different direction. We wanted to explore how much infrastructure can we drop and what was the extreme case to make volumetric capture more accessible to users. So the approach was to reduce the multi-view setup to a single camera and still allow for 360-degree reconstruction. Now, the idea was we get the unknown information from the sides that you cannot see using a previously seen calibration sequence of the person, which could just be the person turning around once in front of the camera in any arbitrary pose. So in the worst case, if the input view was the back of the person as shown in the bottom, we wanted to synthesize all the other views, which were even including the front of the person, and we wanted to figure out, is this even possible? Turns out it was possible to some degree, and as this is a predicted view. So this was the pipeline: the input RGB and depth go in, the calibration sequence previously seen. The pose did not matter too much for the calibration sequence. And this goes into our system, and a novel viewpoint rendering is synthesized. So this pipeline had multiple stages. For example, the first stage would actually take the RGB and the depth from the current view and project it to the target view. The second stage would choose the best calibration image given the viewpoint of the person that we wanted to synthesize. And finally, there were two learned stages, which warped the calibration image to the correct pose. And then finally, a neural blender took the output of the first stage and the calibration image warper and blended all of it into the final viewpoint. So I won't get into details, but I refer you to the paper if you would like to know more. Now, the results here were plausible when you looked at images, but there were lots of caveats. There was a lot of temporal flickering in videos, and then you saw that the hands were missing for the person because the hands were actually not captured by any of the cameras in that viewpoint during training, because the capture setup was not able to look at the entire person in certain poses. So, but it generalized reasonably well to like unseen people as well. And, you know, it was encouraging given how difficult the problem was. Here we quickly show the viewpoint generalization as well. Similarly, some issues with temporal stability. So what we realized at this point was that we were kind of limited by the quality of our data sets. So we invested some time in improving our capture setup and basically collecting a much better data set. So the old data set stats are given here, you know, much lower resolution cameras, fewer subjects. The new data set had way more cameras, much higher resolution, and a lot more subjects. We also switched to an offline reconstruction method, the Relightables, rather than the motion diffusion that was used for looking good. So this is a quick example of what difference this made in the quality of a reconstructed mesh. The old mesh, Christoph, is barely recognizable on the left, whereas in the center, the new mesh from the Relightables with baked-in lighting was actually quite close to the ground truth. So the natural thing to try was to extend looking good using the new meshes. And this worked fine. If the new mesh was the input and the ground truth image was the output, looking good worked great. But we also wanted to add relighting to such a framework. And that required the mesh to be rendered in the target lighting condition. Now, the Relightable meshes that needed to be rendered in the target lighting condition needed to come from the gradient images in order to support dynamic capture, because the person would otherwise need to stand still while one light at a time images were captured, which would take much longer, and the person couldn't move. So now this led to certain loss in quality in the rendered mesh because there was a handcrafted BRDF assumption and there was some approximate rendering. So now, if you look at the mesh with the baked-in lighting and compare it to a relightable mesh, you see that the relightable mesh is a lot worse in quality. But we could also use this as input to looking good and get relightability and free viewpoint synthesis, which is what we tried. So the predicted is on the left, and you can see the original on the second from the right. And it did pretty good for like seen people, I want to say. There were some issues, but it was reasonable. However, when we moved to unseen people, we saw that an approach like looking good started falling apart very quickly, even when we had a larger data set. So generalization for such approaches, if you coupled them with relighting, turned out to be quite difficult. Now, coming to the crux of our work, the deep relightables. This is the approach that we wanted to design, which kind of did everything that we wanted to capture and give us better quality and generalization. So the idea for deep relightables was that we'll take multiple images, gradient images from multiple viewpoints, And then we are able to synthesize arbitrary viewpoints, seen in the top row. We're able to synthesize arbitrary lighting conditions, seen in the middle row, with OLAT images. It synthesizes here, OLAT image being one light at a time with one light of the light stage on. OLAT images can actually be combined then linearly to compute relit images under any arbitrary HDRI environment. And also, one requirement we wanted to add on here was that this approach needed to generalize to a moving performer, so it needed to support like dynamic captures, and it also needed to generalize to unseen people. So deep relightables was our take on a pipeline, basically, on a deep learning framework that could do all these things. And as far as we know, this was the first neural rendering approach that tackled all of these things jointly. So here's the deep relightables pipeline. You'll see some connections to the relightables, but let me walk you through it. So we take gradient images from multiple camera viewpoints as input, along with their view directions. These go through a feature extractor with shared weights. Then features from each one of these viewpoints is actually warped to a common UV space using pre-computed warps calculated using the depth and the UV parameterization information. Now, once all of these features are in UV space, they are pooled together in UV space in order to be invariant to the number of views. Finally, after pooling, we run one-by-one convolutions and then compute the final neural texture. Now, this neural texture can then be projected back to any arbitrary target viewpoint using, again, a pre-computed warp. And this is where we supply lighting and view direction inputs and finally synthesize one light at a time, or OLAT images, which can then be combined to produce a relit image under any arbitrary environment. So that's the basic idea. Now let's walk through the components of this pipeline. So the feature extractor, as I mentioned, takes gradient image input. Now these gradient images, which is basic, they contain a lot of information. They contain information about the albedo. They contain information about the normals because the light is actually varying in both directions. And they also contain view-dependent effects information because the specular reflections would actually be of different colors depending on the direction you're looking from. And the most important thing is that they enable moving performers, because if you were to capture OLAT images instead of gradient images, the performer would not be able to move for 6 seconds. Now, we also give the view direction as input to the feature extractor so that it can reason about the view-dependent information that is contained in the gradient images. And finally, the feature extractor is in the form of a UNet-like network with certain receptive field. So even if we warp these features using a pre-computed warp that is based on the geometry, in theory, the features can capture slightly more than the particular pixel. So they capture a little bit of their neighborhood, neighborhood view RGB information, which can then be used to reconstruct parts that were not actually present in the geometry. So it can, the features can, in theory, splat back and reconstruct an earring or something that was missed in the geometry. So some properties of the neural texture. As I mentioned, the neural UV features are regressed from the input gradient images. And thus, contrary to deferred neural rendering, there's generalization to unseen people as well as dynamic performance, support where people can move. Another cool thing is that it can support different resolutions at train and test time. Even if we compute these at lower resolution during training, we can compute them at a much higher resolution during test time. I mentioned earlier that the feature extraction is done from multiple varying viewpoints. The pooling of the features in UV space enables us to use a varying number of viewpoints. When we pool these features together, we factor in the camera visibility to weigh front-facing pixels higher, and there's some other tricks. This is independent of the order of viewpoints because it's a pooling operation. And finally, we can train with a different number of views and actually test with all the views. Similarly, for novel view synthesis, you can compute the feature once, the neural texture once, and then compute all novel views from that without rerunning the first part of the pipeline. The important thing here is that it supports changing UV parameterization. In our case, our UV parameterization is not constant in time, and when tracking is lost, it changes. Since the warps are pre-computed based on geometry, if we ran any kind of spatial operations in the UV texture space, we would not support UV changing UV parameterization. That's why we run only 1x1 convolutions, which do not see the spatial extent of the UV texture. Thus, this supports moving performance. So now the neural re-renderer component, we finally take these UV features, resample them to the target viewpoint. This is where we give lighting dependent information, which is in the form of a reflection map, which is basically giving you some information about where the specularities would be, and the light visibility, as well as the view direction. We also add an alpha mask prediction module here and give all this information to a neural renderer, which synthesizes an OLAT, or one light at a time image. Now, there's some things, some details about the re-renderer. Basically, there's view direction input. It enables the reasoning of the view-dependent effects. The light visibility improves the quality and the generalization of self-occlusions. Similarly, the reflection maps improves the quality and the generalization to view-dependent effects. We also output an RGB image at the 1x1 conv level itself and feed that to the re-renderer. What this does is it improves the generalization of RGB colors, because the network is to synthesize, it's forced to use all the information at a 1x1 conv level, or a 1x1 pixel level, and synthesize the final RGB. And thus it prevents the final neural re-renderer, which is a large unit, from overfitting to the textures that it has seen during training. Similarly, the alpha mask prediction enables higher quality and for compositing, and the perceptual losses, which are then fine-tuned with adversarial learning, give us like sharper outputs. So let's quickly look at some results. Here we look at the neural rendering results for view synthesis. You'll see that the quality looks pretty good. The view-dependent effects are looking quite nice. Here we can see the neural rendering results for illumination and view synthesis. So these are novel viewpoints, as well as novel illumination conditions, which are like cycling through. And over here, we can see that it supports dynamic performance capture. The person can move and the temporal stability stays pretty reasonable, even while we change the viewpoints. Here we change the viewpoint and the lighting condition while the performer is moving. These are also unseen people on the sides. Finally, some results for the alpha mask prediction, and you can see that the alpha mask predicted by the network is much better than the mask that we get from the mesh. Here we show some comparisons with other view synthesis methods. There's looking good with baked-in lighting on the left. Our approach does better than that. And in fact, our approach also does comparably to deferred neural rendering with Thies et al. 2019, which actually does not generalize to moving performers or unseen subjects. Similarly, here we compare to Meka et al., which basically deals only with light synthesis, and it basically is an approach of deep reflectance fields that predicts OLAT images and does not do view synthesis. And our approach, even despite doing view synthesis, does a bit better because the geometry information is factored in with the light visibility maps, etc. So you can see the shadow handling and things like that are better. Okay, this is finally some relit images, which shows how much the proposed approach actually improves over the Relightables pipeline. Different performers under different HDRI environments. And finally, let's talk about what we use these neural rendered outputs for. So basically, we've been using them for data augmentation. They can give more viewpoints than you capture. They can give arbitrary lighting conditions. They can give arbitrary backgrounds via compositing with the alpha mask that we predicted. And it also gives us a pipeline which is better than state-of-the-art geometric pipelines in terms of photorealism, geometry, and alpha masks. So these are some of the in-the-wild applications that we've been using neural render data for. There's relighting, lighting estimation, alpha matting, depth estimation, pose estimation, and some of these works might be familiar to some of you all. Some extensions I wanted to talk about was basically One caveat about deep relightable textures was that you need to predict OLAT images. So then you need to basically synthesize about 300 images before you synthesize one frame of a relit image. This can be slow. So predicting relit images directly would be much nicer. And the total relighting work that's shown on the right actually enables something like this. Now, in the total relighting work, what we did was we proposed light map representations, which was something like an RGB extension of the specular map and the light visibility that was used for deep relightable textures. Basically, what we did for the diffuse component of these light maps, we pre-convolved the HDRI maps to simulate the basic, like the aggregation that would have been needed otherwise. And you end up getting like a 3-channel RGB diffuse light map and a 3-channel RGB specular light map, which gives the network information about what colors are present in the lighting in the scene. So the single channel light visibility and the single channel reflection map can be replaced by these, and the prediction can directly be relit images. And this tends to work well. We've done some initial experiments with this. Total relighting will, of course, be presented at SIGGRAPH 21. Please go check out the talk there for more details. We've also been working on depth and correspondence predictions so that the approach deep relightables is not dependent on depth information. And some next steps for us are pose and appearance control as well. So with that, here are a few more final results. And with that, thank you. And please, feel free to ask questions at the session.
Welcome to the session about neural rendering of faces and bodies. My name is Justus Thies, and I recently joined the Max Planck Institute for Intelligent Systems in Tübingen, where I lead the independent research group Neural Capture and Synthesis. My group name is actually closely related to the topic of this course. It's about the AI-based capture of humans, general objects, and room-scale scenes to enable the photorealistic synthesis of novel views, scene edits, as well as the well-known facial reenactment and also full body reenactment. The ability of synthesizing images and videos of humans is of paramount importance for teleconferencing applications in VR or AR, and also allows us to implement powerful movie editing and post-production tools. For both capturing and synthesis, AI-based approaches show promising state-of-the-art results. In the next couple of minutes, I will give an overview of the synthesis of human faces and bodies. As I already mentioned, the synthesis of humans and especially the training of the underlying representations requires motion capturing, either implicitly or explicitly, using, for example, a prior like a 3D morphable model for faces. Both the capturing and synthesis go hand in hand, especially when using approaches that follow the principle of analysis by synthesis. In general, the pipelines of current approaches are very similar and follow a pattern that is illustrated on this slide. Based on a monocular or multi-view video input, the neural rendering pipelines are trained to generate photorealistic outputs that are ideally temporally consistent, which needs to be encouraged by corresponding regularizers and consistency losses. The majority of approaches first applies motion capturing to track and reconstruct a coarse model of the human face or body using priors like a 3D morphable model. Prominent models are the basal face model, or FLAME, and the SMPL model from the Max Planck Institute for Intelligent Systems. These models are used to control the neural rendering process, based on the tracking parameters or synthetic renderings of correspondence maps or colors. Of course, there are also approaches that combine the motion capturing and neural rendering in one method. Prominent examples are the deformable NeRF applications, like NeRFs. They predict the motion field within their rendering approach to reconstruct a neural radiance field that deforms over time. The drawback of such an approach is that you lose controllability that, for example, face and body priors offer. The facial reenactment, where you animate a person with another person's video or only an audio signal, is implicit controllability. The tracking information used for that does not need to have a semantic meaning. It can be some abstract latent code that can be shared across different subjects. But if your motion capturing is using a predefined model, such as a blend shape model, you also get explicit controllability. You can, for example, explicitly modify and synthesize a specific expression. For the motion capturing, there are different representations and strategies. On one side, you have model-based or 3D geometry-based representations that can be estimated either using optimization or a learned regressor. On the other side, you have some sort of codec or latent code that is representing the expression state of the human. Given these extracted motion states, a neural rendering approach can be applied. Depending on the motion capture approach, typical conditionings used are rendered 2D or 3D landmark positions, stick figures, known from Everybody Dance Now, dense synthetic renderings, known from deep video portraits, splattered surface points, known from neural point-based graphics or simple pics, texture coordinates, known from deferred neural rendering, or directly the reconstructed parameters of the tracking or the codecs. In addition to these conditionings, some neural renderer have additional learnable features in the form of per vertex features, neural textures, or an MLP that is either defined on the surface or in 3D space. Based on these conditionings and the learnable features, current neural renderers are either using some kind of image-to-image translation network based on the forward-rendered conditionings, like the 2D landmarks or dense synthetic renderings, or they are using a raycasting method with a learned or fixed integration scheme to produce the final pixel colors, which is basically similar to the NeRF approach. In general, the used underlying representations influence the output space. The majority of facial and full body reenactment methods, for example, assume a fixed view. This allows them to reuse static content, like the background. But ideally, you also want to be able to change the viewpoint for VR and AR applications, and there the disentanglement of foreground and background, but also the disentanglement of illumination, plays an important role. In the following, I will briefly talk about our recent CVPR paper on neural rendering for faces using dynamic neural radiance fields. So, given a monocular video sequence, the goal of the paper is to reconstruct a neural radiance field that dynamically changes for different expressions. This not only allows us to generate synthetic views of the head with novel poses, but also gives us explicit control over the facial expressions. The overall pipeline is very similar to the general pipeline that I already showed. On the left, you can see the motion capturing. We use the optimization-based face reconstruction and tracking pipeline of face-to-face, which gives us the pose of the head, the camera intrinsics, as well as the expression parameters of the underlying blend shape model used in face-to-face. The neural rendering stage uses a NeRF-like MLP that stores the density and color information of the head. In contrast to NeRF, where the MLP is representing a static object, we aim to reconstruct a dynamically changing face. Thus, we additionally condition the MLP with the expression parameters. We embed this MLP into the canonical space of the face model of face-to-face. Using the intrinsics and pose information, We are then able to render the face with different poses. As you have maybe already seen, there are also learnable codes per training image. These learnable codes compensate tracking errors, as well as regions that are not tracked at all, like the shoulders in this case. These learnable codes are actually a really helpful tool, and are also used in approaches like NeRF in the wild to compensate auto exposure, auto white balancing, or other camera recording artifacts in the training data. With this learned dynamic neural radiance field, we can then, for example, run self-reenactment as shown here. In comparison to other reenactment methods, our method results in sharper results, and the head also stays 3D consistent when the pose is changed. Here we show some actual facial reenactment, where a source person is controlling the face of another subject. It is also interesting to have a look at the estimated depth from the integration step. You can see that the representation stores not only the coarse geometry of my face, but also the hair. Of course, the method also has limitations, especially if you render the face from a viewpoint that is far away from the training. Here on the right, you can nicely see the effect of the positional encoding, which results in multiple copies of my head, or at least parts of it. This artifact can be easily resolved by clipping away samples that access the MLP outside the valid range of -pi to pi. So to summarize, I showed the general pipeline for face and body rendering and also discussed one example. Of course, there are many other interesting recent works. Some of them are covered in the following talks by Christian Theobald and Thomas Simon. In general, there are a couple of interesting open challenges. Especially for full body neural rendering, we often see insufficient motion capturing that results in blurry or temporally unstable results. In a recent work called Dynamic Surface Function Networks, I also worked on the topic of improving the motion capturing of human bodies. The goal of this paper is to reconstruct an avatar of a person based on an RGBD input sequence. And the goal is that we reconstruct not only a static human avatar, but an avatar that dynamically changes its surface based on the different poses. So given RGBD inputs shown here on the left, we want to reconstruct a surface of the human here shown on the right, which then looks like this. And you can see that this surface, the reconstructed surface, contains all the pose-dependent effects like wrinkles. And the nice thing about the representation that we are using here is that we are able to control it later on. So we have a controllable character, which also includes these wrinkle details. The idea of the paper is as follows. Given a coarse reconstruction using the simple body model, we want to model the actual surface of the human. And the surface is represented by an MLP. This MLP has a similar structure as the NeRF network and gets positions or surface samples of the simple model as input and predicts the actual surface. So in the canonical space of the simple model, we can sample arbitrary points on the surface, and this MLP gives us the actual correct position in this canonical space, and then we can apply forward skinning to get the actual point in 3D in the post space here. Similar to the NeRFs approach that I showed previously, the MLP is conditioned on the pose. So depending on the pose, the MLP is able to output different offset surfaces. The simple model as well as the MLP parameters are optimized in an analysis by synthesis manner. So given the RGBD input, we reconstruct the simple parameters and we optimize the network in parallel. And here on the right, you can basically see how the reconstruction evolves during optimization time. So it starts with the simple surface, and then you can see that detail is integrated on top. And you can see that you can get the detail from all sides. Note that this is based only on a monocular RGBD sequence, so we don't use any multi-view data here. Here you can see a sequence where you also see the side views here, the normal renderings and the phone renderings. We also show that it works with really low quality RGBD data, like from one of the first Kinect sensors, which you can see here in these results. So you get a really nicely reconstructed mesh of the human here. And based on this representation, like the simple model plus this surface MLP, you can then animate these reconstructed avatars, which you can, for example, see here, where we apply a jumping jacks motion from the MOSH dataset. As a next obvious step, we will also integrate the color reproduction into this network. At the moment, this is only for the surface reconstruction, but it is also quite simple to add color to the MLP, such that we also predict color informations. With that, I'm at the end of my presentation. Thank you for your attention. If you are interested in the field and want to work with me, please feel free to write me an email. I also have several open PhD positions, and I'm happy to start new collaborations.
Hi, I'm Christian Theobald, and I'm the director of the new Visual Computing and AI department at the MPI for Informatics in Saarbrücken. I will tell you about work that our group and the community did on neural rendering and video-based animation of human actors. This part of the course shows that neural rendering creates new possibilities for the video realistic 2D and 3D animation of human characters. These are two examples from our work which illustrate this. The possibilities enable, for instance, control of an actor in video with a computer animation skeleton, or enable a bullet time fly around from a single video. They also enable creation of a video realistic, fully animatable 3D character as shown on the right here. There are a lot of exciting related works on this topic, and here I can merely show a small selection of them. Some methods create novel poses from single images using sparse 2D model knowledge for conditioning, for instance, 2D key points or 2D skeletons. Such conditioning is easy to compute, but artifacts like missing limbs can hardly be prevented, and full 3D and viewpoint changes are harder to achieve. Other methods use denser scene knowledge, like a coarser projected or 3D reconstructed parametric model of a human. Such stronger conditioning can help to enhance visual quality, also under more difficult edited poses. Other methods build animatable characters from multi-view video. A bit earlier in the literature, there were non-learning based approaches that often use combinations of an explicit rigged character mesh and multi-view texture retrieval. The left is an example from our work. The right is an example from the University of Surrey. With such earlier approaches, real-time performance and generalization to larger range of motions is more challenging to achieve. Finally, there are learning-based approaches using multi-view training data. They use neural networks to learn the warping of input views into a target view, or to learn surface appearance on a detailed proxy geometry, or other methods learn human representations as implicit fields. In the following, I present a new single view and a new multi-view approach from our recent work. Let me first present a new method we developed together with friends from Braunschweig University. It is a new framework for high-fidelity neural human motion transfer from monocular video. It handles deformations of clothing in a temporally coherent way. This is presented at CVPR 2021 as an oral paper. Given a single monocular RGB video of a target person, our method is able to reenact this person through the motion performed by another source video. Here we use an image-to-image translation approach. To handle the target actor's clothing in a coherent way, we explicitly estimate the actor's shape, internal clothing structure, and resulting appearance under a given source input pose. Here is an overview of the approach. Given 2D representations of source motion sequence and a static background image, our method synthesizes the target actor's appearance for the provided poses. Instead of performing image generation in a single step, we decompose the pose-to-image translation task into better conditioned cascaded processes where the final appearance is conditioned on intermediate representations of increasing complexity. In the first step, we apply a shape estimator that estimates the target actor's 2D shape in the form of dense body part segmentation from the provided pose. This representation provides direct information on the position of different body parts and can model the deformations of loosely swinging garment independently of the final appearance. To improve temporal consistency, we process the sequence sequentially and feed back previous predictions in a recurrent fashion. As body part segmentations do not provide information about the internal deformations within the clothing, we apply a second translation network that estimates the internal structure of clothing as direction and confidence of local gradients. The resulting clothing structure estimates the state of wrinkles and texture pattern deformations that are crucial for visually appealing motion transfer. Conditioned on the actor's 2D shape and clothing structure, we estimate a target actor's appearance under a given input pose. In contrast to recent approaches, the intermediate estimates help to preserve fine details on non-rigidly deforming clothing and allow for interesting style editing applications, as we will show later on. Finally, we apply a shallow refinement network that fuses the target actor with a background image and generates realistic pose-dependent shadowing. This results in a photorealistic rendering of the actor on the static background. For our experiments, we capture videos of up to 10 minutes showing target actors in a variety of clothing. Our dataset comprises of simple jeans and t-shirts, swinging skirt, a loose t-shirt, as well as two dresses with more complicated texture and wrinkle patterns, as well as a hoodie and a shirt. We make this dataset publicly available. Additionally, we test our method on the dataset from our own previous work featuring 4 actors in tight clothing. Here we show results for several reenactment scenarios. Note how our framework produces temporally coherent representations of 2D shape and clothing structure, which result in realistic swinging of the actress's dress and preservation of high-frequency details in the rendered wrinkles and textures. Our method is able to transfer motion between subjects of different build and gender while keeping the original target identity. Here we show motion transfer result of Pix2Pix HD, Recycle GAN, and the Everybody Dance Now approach by Chan et al. These methods are able to produce photorealistic renderings of actors in unseen poses, but frequently fail to model the dynamic swinging and consistent texture of the forming garment. They also produce other forms of artifacts, such as semantically incorrect background blending and slippery legs. Our method more gracefully handles deforming clothing due to explicit shape and structure prediction, which achieves the most realistic and temporally coherent clothing behavior during the reenactment. Here I show some of these comparisons again side by side. The findings I just reported are also supported by a user study in which the majority of users prefer our results in terms of realism and overall quality. Here we show results on the dataset of Leo and colleagues who perform motion transfer using a pre-captured template mesh of the target actor, which requires a recording of a static actor, mesh reconstruction with structure for motion, and a more sophisticated post-processing. Our method, on the other hand, only requires a monocular training video and achieves comparable quality while outperforming recent video-based performance cloning methods, such as Everybody Dance Now. Our method can be applied for garment style transfer, as image generation is conditioned not only on the actor's pose, but also the estimated clothing layout. Our framework allows to transfer the style between clothing of similar type, like the 2 dresses in this example, by applying the original shape and structure from the driving video on the left. Here we exchange the shape and structure to generate a hoodie in the style of the original shirt. Note how our framework maintains the target actor's appearance, including the sunglasses. Our framework allows to change certain properties by manually manipulating the predicted clothing structure. In this example, we use a constant factor to alter the intensity of wrinkles in the skirt during reenactment. Here are a few more results that are slowed down a bit to show the details better. The second paper I want to briefly discuss is real-time deep dynamic characters, which we present at SIGGRAPH 2021. This is work we did together with friends from Facebook Reality Labs. We propose a learning-based method that creates a 3D character with motion-dependent geometry and motion and view-dependent dynamic textures from a sequence of skeletal body poses. So the input to the method is what you see here on the left, and on the right-hand side, you see the output. Our method takes a 3D skeletal motion as input, here acquired through a multi-view markerless motion capture system. Then our method predicts the dense deforming geometry of the actor conditioned on the motion. These also include some learned dynamic effects, such as cloth swinging. It also predicts the dynamic texture, which is not only conditioned on the skeletal motion, but also on the camera pose. This allows our method to not only capture motion-dependent appearance effects, but also view-dependent appearance changes. As our characters look highly realistic, they can be used for several applications, such as video synthesis, where one can augment a real video with a synthesized character. Also, as our approach supports real-time performance, it can be used for interactive character editing. Here, the user is modifying the skeletal pose, and our approach immediately synthesizes the corresponding 3D photoreal character. To build such an animatable character, we require data from a multi-camera green screen studio with synchronized and calibrated cameras. With that, we capture the subject performing various motions and extract the respective foreground masks. For all frames, we acquire the skeletal pose using a markerless motion capture system. Now let's take a look at our character representation. We assume a 3D template of the subject is given. It features a skeleton, a coarse deformation graph, and a fine-scale surface mesh. The skeleton is parameterized in terms of joint angles and global pose. The embedded graph is parameterized with the node positions in the rest pose, as well as a per node rotation and translation, which allows to deform the graph and the underlying template mesh. Finally, the fine-scale template mesh can be represented with the vertex positions. Now let's check how we use this body model in our method. Our method uses deep neural networks to predict the motion-dependent surface deformations of a 3D template in the form of embedded deformation parameters, dense vertex displacements, as well as motion and view-dependent texture. Here, these are all visualized in the reference pose of the character. Combining the individual outputs results in a photorealistic rendering of the actor. Our algorithm runs in real time. Now let me show you some results. We can overlay our photorealistic characters onto empty background images. The skeleton here is driving our synthesized character. But also when changing viewpoints, the character looks realistic and consistent across views. Here we show a subject with a different type of apparel. As our synthesized characters look highly realistic, they can be used for visual effects, such as here, where the real actor is fighting its virtual double, which is obtained from our method. Let me show you some more results of realistic animated 3D characters that we created with our approach. If you're interested in more of the work we do on neural rendering of humans, please refer to the website of the new Department on Visual Computing and Artificial Intelligence at the MPI for Informatics. And with that, I thank you very much for your attention.
Hello, my name is Thomas Simon, and I'm going to be talking about neural rendering for animatable avatars. And to give you an idea of what I mean, here's a video of some of our prior work.
Well, what can your face do? Can you show us?
Well, I've always hoped you would ask me that question. So I have some pretty good, I think, mouth movement.
All right, so what you saw in the video is an interaction using avatars. Two people are talking to each other, but they're not in the same room. So we're going to need sensors to measure what they're doing with their body. This gets encoded into a signal that can be transmitted over the network and then decoded and rendered so that it can be displayed as if both people were in a shared virtual environment. And the component that decodes and renders avatars is going to be implemented with neural rendering. So we can think of an avatar as a pair of functions, an encoder that measures what the real person is doing, and then a decoder that renders an interpretation of this code. So for the rest of this talk, I'd like us to focus on learning this avatar rendering function. How do you parameterize the inputs, and how do you learn it from data? So for a single point, its appearance changes with Viewpoint. So we could record it with multiple cameras. If we additionally consider different incident illuminations, we would have to measure appearance changes for all combinations of viewpoint and lighting directions. Now, people are dynamic, so we could consider this as a function of time as well. But because we don't want to do just playback or video, we want to control what the face is doing, it's going to be better to think of this not as a function of time, but rather as a function of some underlying state that describes the configuration of the face and the body. So for example, facial expression and body pose. And these components, viewpoint, lighting environment, and a vector describing state, are going to be the parameters of the avatar rendering function. And for this talk, we're also going to assume that these are person-specific models, so we can condition the whole thing on a particular identity or the data of a particular identity. So the goal then is learning a function that can produce valid appearance for all of these combinations of lighting, viewpoint, and state. Now, for a real capture system, however, we won't be able to capture data for all the combinations, right? We can only use a limited set of cameras, a limited set of lights, and we can only capture a limited number of frames. So the trick is choosing learning architectures that have the right inductive biases, that will learn from a limited set of samples, but still generalize to all of the unobserved combinations. And for viewpoint, we call this ability to generalize novel view synthesis or view interpolation or free viewpoint rendering. For lighting, we might call this relighting or light stage super resolution for the case of view interpolation. And then for generalizing states, we talk about being able to animate these models or drive them. And today I want to focus on these last two axes. So First, I will talk about generalizing along light samples to build animatable, relightable faces. And then I will talk about driving signal-aware full-body avatars, which is about generalizing across animation states. All right, so let's jump right into the first part. This is based on work done mainly by Cy B while he was an intern with us, and is a paper in this year's SIGGRAPH. So before we look at the full function, let's consider a simpler setting without the light variation. And this is the setting that Stephen was describing earlier, where multi-view capture system can capture a set of facial expressions, and we can build an avatar that interpolates across viewpoint and expression by tracking a coarse mesh of the face and learning a decoder that generates this mesh and a view-dependent texture map that can be rendered onto the mesh. And we can learn this model by using a variational autoencoder, where the state is a 256-dimensional vector, and the texture decoder architecture is a convolutional neural network, as Stephen was describing before. And the encoder is almost symmetrical, but because we have all viewpoints, we can use an average texture. And this means that the state is not dependent on viewpoint. So we don't need to disentangle the state from the viewpoint codes. And here's a visualization of some of the dimensions of the learned expression code or state. And if we order them by the variance of the training samples that they explain, these look fairly similar to principal components of a 3D morphable model. So a lot of the conclusions from Blanchard work, for example, will translate into this setting as well. All right, so now if we add the dimension of light variation, we're going to have to acquire training samples with light variation so that we can learn the appearance function. And our capture system is very similar to a light stage. We have controllable LED lights that can be turned on and off to create different illumination conditions. But if you think about what is the ideal data capture, it would be one where we can capture all possible illumination conditions. And this is clearly not practical, right? Because even just capturing each light turned on and off one at a time is an increase of 460 of the captured time, right? The 460 is the number of lights we have. So this would be too much. So instead of doing this, we're going to approximate this by capturing dynamic expressions as before, so the subject is just doing things with the face. And we choose a light pattern that maximizes light variation. So we're going to rely on amortized inference during model building to generalize to all of the unobserved light conditions. And additionally, because we have to track the face, we're going to interleave fully lit frames, right? So it looks like this. We have these interleaved fully lit frames, every third frame in this case, and then two interleaved illumination conditions, in this case one light at a time or something similar, in between. All right, so now that we have the training data, we can try the same architecture as before, where we simply add the light code as an input. And because we're adding this code at the beginning of the decoder, we call this early conditioning. And to parameterize the light code, we're going to assume distant lighting and use an environment map. So we discretize this environment map to a grid of 32 by 16, which we can then vectorize. Now, if we train this model on the light stage data and try to run it on real environments, it doesn't work. It just looks very bad, right? So what's going wrong here? Now, if we look at the training error for this model, it's actually not bad. The problem is the architecture is not generalizing. We've trained only on light stage data, which is monochrome, has one light turned on at a time, has these discrete locations, but we're testing on natural illuminations, which have like color and continuous radiance, right? So that's very different. So instead, we're going to introduce a different model, which we call late condition, which has better generalization. So compared to the early condition model, where the light information is input at the beginning of the CNN, the late condition model is going to condition light information towards the end of the network, right before you produce the color of each texel. And the reason this model generalizes better is because we can directly incorporate the additivity of light into the network architecture. So if we look at a single texel, to produce the final color, we're going to sum up over each light direction. So this is going to be the 460 lights in our capture system. And we're going to directly multiply each light contribution by its corresponding RGB intensity. So the MLP function doesn't have to learn all these properties of lights, and it only has to learn a light direction dependent gradients. So we parameterize this MLP as a function of features that are decoded using viewpoint and expression, and additionally the corresponding light direction. Now, this works, but we found that we get even better results if we make the network's job easier by adding a shadow map feature. And this helps make sharp shadows on the neck and on the nose here. So this is similar to computing a geometric shadow using the coarse mesh, but because we know the mesh is not perfect, instead of doing this, we compute the depth difference that would be used to compute the shadow map. And then we use this as the shadow map feature at each texel. And then the MLP can learn to use this feature. And this works well, but the only problem is that because we are summing over all of these light directions, this late condition model is very slow to evaluate on environmental illuminations. So instead, what we can do is use this late condition model as a teacher network to produce synthetic images under these natural environments, and use these to train the early condition model, which is very fast to evaluate. So this is what we're showing here. On the left is the late condition model, and on the right is the early condition model trained on synthetic images of environment maps produced by the late condition model. So what we have now is a fast model where we can change each of these inputs independently, lighting, expression, and viewpoint, which means that we can use a driving signal, for example, obtained from a set of cameras on a headset, and then render the corresponding avatar in a new environment from arbitrary viewpoints. All right, so that wraps up what we had set out to do for relightable faces. And to recap, the main idea here was to find a network architecture that can generalize from a limited set of samples in our training data, in this case, by exploiting the additivity of light and amortized inference during model building. So now I'd like to switch gears a little bit and forget about lighting and instead focus on the state axis. So this is going to be the problem of generalizing across the state space. And this problem becomes more apparent when we're building full body avatars. So for the second part of the talk, I'm going to talk about driving signal aware full body avatars. And this is work done mainly by Timur and is also a paper in this year's SIGGRAPH. So the core problem here is very similar. So instead of having to generalize from light stage illuminations to natural illuminations, we have to generalize from a small set of motions in our training data to any arbitrary natural motion that you might want to do at test time. And because the combination of each degree of freedom can be done independently, there's a huge space, right? So the animation setting I'd like you to consider is an example of performance capture. So on the left is the rendered avatar, and on the right is the signal we're going to use to drive the animation, which is joint angles for body pose and face key points for facial expression. So let me play this video.
Yeah, I really want a French bulldog. That's what I want. I just want to take it for walks and love it and squeeze its little face. Oh, I just want a dog so bad.
All right, so the thing to realize here is that the animating an avatar is often asymmetric. The person driving the avatar can wear different clothes or have a different hairstyle, but we still want the avatar to look photorealistic. So if we consider the driving signal used to create this animation, in this case it's facial expression and body pose, it's going to be an incomplete representation of the full state. For example, it says nothing about the clothing. So this implies an asymmetry in the data we use in the driving signal component and for training the neural rendering component, because recall that the neural rendering component is learned from a multi-view capture system. So the amount of information contained in the training signal is going to be more than what is available for driving. And this could be because the performer is wearing different clothes, so there's asymmetry in the content. Or it can also be, in the case of a telepresence application, that the asymmetry is because the sensors are not going to be able to capture a complete signal. So in this video, the facial expression is going to be driven by the cameras on the headset, and these cameras don't observe the hair or the back of the head, right? So let me play.
Cranky, and like this is not something that has ever happened to me before. Like I used to be like, yeah, 95 degrees, this is wonderful, and now I'm like, oh, it's 82. Is anybody feeling a little hot?
All right. So note also that we're not trying to reproduce the face with the headset, but rather how it would look without the headset. So there's still asymmetry in the content. But what we have at any rate is that the driving signal is going to be an incomplete representation of the total state, either because the setting is different or because we are limited by our sensors. So to fully describe state, we're going to need additional signal, which I'm going to call unobserved state for now. And this is going to capture state that is not deterministically determined by the driving signal. So what does this unobserved state capture? And if we fix the pose, this is the effect of changing the vector that represents this unobserved latent space. And you can see that what it captures mostly is clothing variation, like wrinkles and the configuration of the shirt. All right, so let's look at how we build these models. We follow a very similar procedure as for the face. So we use a multi-view capture system, this time bigger, to capture the entire body. And then we use a body tracker to track the mesh, the body pose, meaning joint angles, and the facial expression. And then, again, we're going to use an autoencoder to learn the decoder. But instead of assuming that the state representation of the decoder is complete, we're going to split this state space into the driving signal, which comes from the body tracker, and some additional latent space that explains the remaining information. And to avoid unwanted correlations from our limited training data, we are going to ensure that the mutual information between these two components is low so that they are disentangled. And I'll give a brief overview of the decoder architecture to give you an idea of how it works. Now, this decoder is more complicated, but I'll step through each component. So the decoder itself is similar to the face decoder. It's going to be a transposed convolutional architecture that takes state and an encoding of view directions and produces geometry and view-dependent texture. But this time the geometry decoder is going to first decode geometry as a displacement map in UV space. The vertices are then sampled to produce an unposed mesh. And then we pose the geometry using the body pose angles using linear blend skinning. Now, additionally, to account for shadows, we're going to compute a shadow map. And using the mesh, we're going to compute ambient occlusion geometrically. But because we know this is only an approximation, we're going to use a U-Net network to learn to transform this into a shadow map. And then this shadow map is going to be multiplied by the texture map. And finally, we're going to use differentiable rendering to render the model and compute L2 loss with respect to a real image and also with respect to the tracked geometry. All right, so this video here shows the effect of the shadow branch. And notice that when using the shadow branch, the shadows are much better represented in the final model. All right, so the driving signals are pose and facial expression, as we said before, and they come from the body tracker. But we rearrange them spatially to ensure locality of influence of each component. So, for example, we don't want the right arm joint angle to affect the left arm. And finally, the latent code of an observed state is learned using an autoencoder from the tracked meshes. And we're going to disentangle the driving signal from this latent code to ensure that the mutual information between these two spaces is very small. And if we don't have this latent space, or we don't disentangle it from the driving signal, we start seeing these correlation artifacts when driving new motions that are not in your training set. So let me show one final example.
This soccer is pretty simple, right? Just one ball, two goals. So this is soccer with these like little rocket-powered cars, and you control them, and like they go and they can like fly, but only for a limited time.
All right, so I'll wrap up here. And to summarize, we saw that to render avatars, we want to produce any possible combination of viewpoint, lighting, and state, but we have to learn this function from limited training data. And we saw a few examples of how the choice of the learning architecture can achieve better generalization. So for lighting, we did this by incorporating the additivity of light into the architecture. And then for bodies, I explained how being driving signal aware can avoid some of these spurious correlations when animating from limited sensing data. So for more details, I recommend catching the presentations of Timur and Sai in the main conference, and thank you for your attention.
Hello everyone. You've heard a lot about cutting-edge neural rendering today. Now it's time to discuss some open challenges. My name is Ohad Fried. I'm an assistant professor at IDC Herzliya, And today you've heard from all these wonderful people that you see currently up on the slide. And let's get going. So first question, are we done with neural rendering, right? Is everything solved? Of course not. In fact, it was really hard to pick which open challenges to talk about today. Some of my colleagues have already mentioned a few, so I decided to talk about what I believe to be two very interesting and pressing open challenges. The first one is about playing nicely with other representations. What do I mean by that? It means how do we incorporate neural rendering into the way we currently do rendering. More details to come. Second challenge is about editability and controllability. While neural rendering has come a long way, definitely, in the past 2 years or so, it's still way easier to edit and to animate good old-fashioned polygonal meshes. Okay, let's start with the first challenge. As we all know, rendering systems are comprised of many different pieces. Right? We have the ways that we represent shapes, such as polygonal meshes and volumes. We have material properties and texture. We represent light and light sources, have different rendering methods. And for specific objects like fluids or crowds, we use simulation to produce animation. A hodgepodge of things, right? At the end of the day, when you open a software suite like Maya or like Unreal Engine, all of these parts come together very nicely to create a rendering machine that we perfected for years, right? So the question now is, how does neural rendering fit into all of this pre-existing infrastructure and methods and ways that we developed? Now, if you ask me, neural rendering is in its teenage years. And what do I mean by that? I mean that we are well past the infancy stage. That stage is where we created awesome research that was groundbreaking and taught us a lot, but it was far from being practical. We're talking extremely slow, extremely specific systems that really cannot coexist with other rendering pipelines. Now, neural rendering is a teenager. It's still exciting. Plenty of research opportunity. Some of the research should try to get neural rendering to actually work. And indeed today we've seen great strides in that direction in the previous talks. And you should really ask yourself, what does a neural rendering component inside Blender or inside Unity, what does that look like? And it's not just about engineering. Right? The engineering is far from being trivial, but we really need to answer some deep questions here. For example, when you want to mix polygonal meshes with neural rendering primitives, first of all, we need to ask ourselves, okay, but what is a neural rendering primitive? How to package, use, share such primitives? What is it, this beast? Currently, we have all these different methods, but it's not. There's no one way of describing neural rendering primitives. Next, we need to find a way to cleverly use each method according to its strengths and weaknesses. What I mean by method, I mean neural rendering versus other representations, other ways of doing things. So when do we use neural rendering? When do we use something like polygonal meshes? Maybe the decision is not binary. Maybe the same object can be rendered in both ways or in more than 2 ways, depending on, for example, let's say viewing distance. How do we efficiently render this mishmash of ways to represent objects? And lastly, how do we bring neural rendering primitives to the same level of editability and animation capabilities that we are used to when working with polygonal meshes. Let's dive in a bit deeper on that last point. So, editing appearance and animating. We've seen some exciting progress today when it comes to editable neural rendering. Under some conditions, we can edit lighting, camera location, materials, other properties. However, there's still a gap when we compare to traditional rendering. Personally, I think that we can really gain inspiration from traditional editing workflows and investigate how to reproduce them under the very different rule set, which is neural rendering. I think that's the exciting research here. So that was kind of quick because we don't have a lot of time. I mentioned 2 open challenges, but are those the only open challenges? Of course not. And in fact, throughout the day, you've heard of many other open challenges. But our time is almost over. So in the few minutes that I have left, please allow me to do a short recap of what you've seen throughout the day. We started the day with Michael's talk, and he gave a definition of neural rendering, right? Deep neural networks for image or video generation that enable explicit or implicit control of scene properties. By the way, I wrote here a definition, not the definition, because maybe there's more than one. Maybe we should still think about what is the definition of neural rendering. Let's take this at face value for now, and let's break up the definition again. So we're talking about image or video generation, meaning that we synthesize pixels. Although, by the way, a really exciting direction for future research is multimodal rendering, meaning that together with pixels, we also synthesize, for example, audio. When we say explicit or implicit control, we control the output either by a set of interpretable parameters, interpretability is extremely important, or by providing some conditional inputs. For example, providing text or audio or video, something which should condition the output to be what we want it to be. Scene properties, what do we mean by that? Well, everything you can think of, right? Illumination, camera, pose, geometry, appearance, semantic structure, animation, really anything that a user would like to control. It's been a long day, right? Throughout the day, you've heard about the latest and greatest in neural rendering, at least some of the latest and greatest. After the intro, we talked about GANs and how they relate to neural rendering. Then we discussed the problem of novel view synthesis. After that, we discussed light and relighting. And next, we talked about compositional neural rendering, followed by methods for free viewpoint video. And lastly, we zoomed in on synthesis of humans, right? Both faces and body. It was my pleasure to extremely briefly mention some open challenges. And right after me, Manish will discuss the ethical implications of neural rendering, also extremely important. And if you're interested in a follow-up discussion, please join us for the panel discussion and Q&A. Most of the authors, most of the presenters made themselves available for questions, even though for some it's really weird in terms of the time zone. So please join us. With that, I want to thank you all for listening. That's it for me. I can't wait to see what all of you, come up with next in terms of neural rendering. If you want more, please check out our website, and have a great conference.